So 3 is a new unit for us, and we're going to start talking about camera models. And it's going to start off gentle and then get a little rougher later, where we start to get into things like perspective projection. So just bear with us. In the middle, we'll do something cool in stereo, which you're actually going to do for a problem set, and it's pretty straightforward. But that's what this class will keep trying to do. We'll dive down into the math a little bit, come back up, try to make sure you always have the math you need for doing the problem sets. Some of the stuff we'll give you won't use directly on the problem sets for the assignments or even the exam, but it's important that you know about it. So what is an image? Well, up until today, we've been talking about images as functions. Remember, they were a two-dimensional function, or a function of intensity of 2 dimensions, x, y, u, v, I, j. Today, we're going to start saying, wait a minute, it's not just an arbitrary function. These images are actually projections of 3-dimensional scenes, of 3-dimensional points. Here is an example of the first known photograph. It's one of the first known recorded projections, done in 1826. You can see the device here on the left, and on the right was a reproduction that was made in the mid-50s of what the image looked like. Now, what's remarkable is this image is called a heliograph. Helio-sun, because it took a lot of sunlight in order to make that picture. A pewter plate, which is metal, was coated with something called bitumen of Judea, which is some sort of derivative of a petroleum chemical. After a day-long exposure, so like 8 hours, the plate's removed, and the image is found by, you have to wash it in a solution, a mixture of oil, of lavender, and white petroleum, which dissolved away the parts that had not been hardened by the light. So the idea was you have a chemical, it was a liquid that underwent a chemical reaction from the light that would change it, so then you could then remove some of it, and that's how you got an image. Those of you who've been fortunate enough ever to work in a dark room, it still has that principle of chemicals manipulating silver halide or some silver elements that are changed by light. Of course, most of us don't do that anymore. We use these fancy devices which have no soul, but which capture pixels better. What is a camera or an imaging system? So, simple definition is it's some device that allows the projection of light from 3 dimensions, 3-dimensional points, to some medium that will record the light pattern. That medium can be film, or it can be a sensor, etc. But actually the key word to all this is projection. So here's a projection, some people walking on a sidewalk, and there's this globe-like thing in the middle, and something that might convince you that something is a little strange might be, there's a tiny little guy standing on top of the world. This was a pre-clip for the movie Titanic. That was a joke, tiny little guy, Leonardo DiCaprio is not so big. Okay, anyway. What's really in that picture is that. Okay? And the reality is, this picture wasn't actually the projection that you thought it was, so at least some of you. So you thought maybe it was like this ball thing that you were looking at an image, and no, actually it was a flat thing that happened to be projecting into the camera. And that gives you an idea that when you do projection, somehow you're losing information, you're losing 3 dimensions, the 3rd dimension, you go from 3 to 2, and we have to figure out what went on in that 3rd dimension. Let's talk about how you might make an image. So here's an idea. Let's just take a piece of film or a sensor, and let's just expose it to the light. Do we get a reasonable picture? Well, and the fact that the title says image formation bad method should give it away. Well, this point on top of this cartoon pine tree, well, it projects a ray of light to some point on the film, but of course it also projects a ray of light all over the film. Likewise, another point projects all over the film. So one of the problems is that every location on the film is seeing light from all sorts of different places. There's no single value of light that comes from a single place in the world. So how might we fix that? Well, here's an easy way. Let's put in a barrier with a very small hole in it. So here we have this little hole, and it's called an aperture. Okay? And we're going to use the word aperture to mean a couple of different things, but in general, the aperture is a small hole that lets light in it. You might change the size. But here we have an aperture, and what that aperture makes is that each area on the film plane or on your sensor plane is seeing light from only one point on the object. So it is showing you the light that just came from one place in the world, which is what we're after. By the way, something to note here, and we're going to see this a lot more, is that the image over here on the film is inverted from what's on the object. So the pine tree would be upside down, if you will. The very first known camera, that is not something that the film recorded, but camera, is actually dates back to Aristotle. And here's an image, and it's called camera obscura, which is from Latin, means darkened room. So those of you who speak any Romance language, comma, bed, camera from room, obscura, darkened room. By the way, there's a cool museum in Edinburgh called Camera Obscura, which is all about the history of cameras and photography. I highly recommend it, although I didn't go there because I was in the Scotch Museum. And here you see the idea of a room with also a small hole in it. Okay, that's the aperture, projecting on a white wall in the back. In fact, there was a nice quote from Da Vinci. I don't know how you get quotes from Da Vinci, but I guess he wrote them down. Or maybe it was on Memorex tape, I don't know. It says, when images of illuminated objects penetrate through a small hole in a very dark room, you see, on the opposite wall, these objects in their proper form and color, reduced in size in a reversed position owing to the intersection of the rays. Okay, and that's what we were showing before. And by the way, those of you who think about lenses and focal length, the focal length of that system was the depth of the room. All right? So how does that aperture affect the image that we see? How does the size affect the image? Here's a demonstration taken from Paul Debevec's website of making pinhole cameras. And you can see on the left that he actually took a piece of foil and he's mounted it directly on an electronic imaging system. On the right is the picture that was produced using this camera, and presumably he had to worry about leaving the shutter open long enough to get the proper kind of exposure depending upon the sensitivity of the sensor, and we're not going to talk about imaging and sensitivity in this course. The first thing you might notice is, boy, that's an awfully blurry picture. And the question is, why so blurry? We just said that when we put a really small hole, it only lets a single ray of light in, and so it should be nice and crisp. Well, the problem, of course, is that there's small and then there's small. And so the question is, how big should the aperture be? So here is an actual rendering using a pinhole type camera, where they're showing you the different size of an aperture in terms of millimeters, and the ability to see a crisp image on the other side. And you notice when it starts out at 2 millimeters, you get a pretty blurry picture. And another way of saying that is 2 millimeters is large compared to the rays that you want to try to capture. And then it goes down to 1 and 0.6, and finally 0.35 millimeters gives us a pretty nice rendition. So the question you might ask is, well, why not make the aperture as small as possible? I mean, the smaller I make it, the smaller number of rays that get through and the crisper it will be. And the answer lies in, let's see, somewhere in physics. Maybe you played with water tanks where you cut little slits and you pushed waves through them and you caused ripples to change. And then you learned about something called diffraction, okay, and how waves interfere. And with light, what happens is if you make those holes too small, you start to get diffraction effects. So at 0.35 millimeters, we had a nice crisp picture, but then things start to go bad, and then when it gets even smaller, not only are we getting less light in, but we're starting to get things blurred out again, and that's because of diffraction effects. So you have to worry about those kind of things if you're making pinhole cameras. The rest of what we're about to do for this lesson is just talk a little bit more about some of the properties of image formation in lenses and cameras. Actually belongs more in a course called computational photography. And my colleague Irfan Issa at Georgia Tech teaches one, and there are others online. And it teaches you sort of the math of photography. I'm only going to talk a little bit about it here, because next time we'll sort of run back and revert to a very simplified model of imaging and do a much more complicated notion on recovery of computer vision. So the first thing about computational photography is, well, we don't actually use pinhole cameras, right? We use lenses. And lenses have this notion of focus. And in general, lenses are designed so that all the points at a particular distance away will all be focused to the same point on your film or on your recording medium. One of the challenges there is that another point that's at a different distance away, so here the blue point on the tree, they're not all going to be focused at that point. They're going to be sort of spread out a little bit. And in fact, that spread is referred to sometimes as the circle of confusion. If it's a single point, there's a circle that it cuts out. So the way you change where things focus and how much is in focus have to do with changing the shape of the lens. So talk just a little bit about lenses. Sort of our slightly simplified view of lenses is as follows. One is that lenses have an optical axis along which light passes straight through, unbent. The other is that light that comes in parallel are all bent to the same point, and that's referred to as the focal point. The other thing is, in order to reduce the amount of spread and things, lenses also have an aperture. But now the aperture, instead of being just a single point, is restricting the set of rays that are coming in. It used to be that almost all lenses were cut out of parts of spheres because we understood the mechanics of that and were easy to make and you could do the math. But these days there are many what are called aspherical elements because it's all computer modeling. We'll talk about that just a little bit at the very end. In computational photography, it's common to make what's known as a thin lens assumption. So a thin lens assumption is basically the drawing that I just showed you before, where we say, okay, for a given lens with a given focal point, it's going to image some object at, let's say, distance d0 at some distance di, or for d for image, back. And the question is, can we predict from the focal point what the relationship is between d0 and di? Well, obviously the answer is yes, or I wouldn't have been wasting all this film, or I waste your time. So here's a thin film lens diagram taken from the slides by David Forsyth for their textbook. And we're going to use that to derive the relationship between the distance in the world, and which we're going to call here z, away from the center of the lens, to the distance z prime, which is where the image will be focused, and the focal length f. First, just to be clear, here is some point P. That's at some height y, since we're just going to look at the side. We're going to assume that it's projected at some point P prime, that is y prime off of here. And here is our focal length f. All right, the idea is that all parallel rays are going to intersect f, okay, which is why this one goes back here this way as well. All right. So when we have all sorts of parallel lines and that are going through the same point, it's easy to reason about what's going on here using similar triangles. So here we have our similar triangle, and it basically says that y is to z as y prime is to z prime. Two things to note here. First of all, I only use the magnitude of z and z prime because we're only going to worry about the length. And I probably could have used the magnitude of y prime, but just to make it clear that the y value is inverted, I said negative y prime as being a positive value. So if y is positive, then y prime would be negative. If y is negative, then y prime would be positive, and thus the negative sign. All right, so that's our first similar triangle. Our next similar triangle is here. And that says, and this one's a little bit trickier, again, the ratio between y prime and y is the same as the ratio between z minus f, so that's this amount, right? All of z minus f is to f, so y is to f. All right, so just look at that a little bit. So y prime, size of y prime is to y, as z prime minus f is to f. So that gives us a second set of similar triangles. Combining these two formulas gives us this formula. Not rocket science here, we're just setting the two left-hand sides are the same, so we set the two right-hand sides equal to the same. We continue, we play around with the math a little bit, and we get this very simple formula, that 1 over the magnitude of z prime plus 1 over the magnitude of z equals 1 over f. That's the thin lens equation, and any points that satisfy that equation are in focus. Okay, so if my film plane on a thin lens assumption or a thin lens model, if my film plane is z prime away from the lens for a focal length f, then everything that is z away will be in focus. So by moving the lens in and out a little bit from my film plane, I change where in the world things are in focus. So I can change the z prime easily. I can move the lens in and out from where my film plane is, and that changes the points out in the world that are in focus. There's a cool little thin lens app. Took me 4 times to say that before I got it right. It's posted here on the web, and it just lets you sort of play around with how you change the geometry of what's going to happen.
Let's try and apply this equation to bring an object into focus. Here's our lens and image plane. Now say we have an object point P that gets projected onto the image plane at point P prime. Now let's complete the thin lens diagram. We know that rays of light from P that are parallel to the principal axis, after refraction, cross the principal axis at a point that is focal length away. So that distance is f. Similarly on the other side, that is also f. The distance of the object from the lens is z, and the distance between the image plane and the lens is z prime. Let's say the focal length f is 50 millimeters. Now consider two scenarios. One where the object is 1 meter away, and second where the object is 2 meters away. At what corresponding values of z prime would the object be in focus? Enter your answers in the boxes provided in millimeters with up to 2 decimal places of precision. As you might have guessed, we want to apply the thin lens equation. Let's make our units consistent by converting z1 to millimeters. Now applying the formula, we know that 1 by z1 prime plus 1 by z1 is equal to 1 by focal length. Solving this for z1 prime gives us 52.63 millimeters. Similarly for z2 prime, we have 51.28.
One of the cool things about real lenses is, as I'm looking at a scene, if I want to, I can just change a little bit the focus in and out. Now, for those of us who use cameras that just take pictures, our goal is to put something in focus or out of focus, etc., whatever. If you're like Megan, who thinks static pictures are like just way old school and the only thing that matters is video, then the idea of changing focus during video is interesting. Generates something, it's called pulling focus or a focus pull, and you get this really cool effect. And here you can see this picture of this, pretty sure that's the water temple in San Francisco. Somebody else might remember. And there's the back end, that's the polite way of saying it, is of a duck. But you can kind of see that it's shot through a fence, and as I run the video you can see how changing focus changes how far in the scene, how far Z has to be in order for it to be in focus on the image plane. And that's pretty cool. One of the important things when you talk about real lenses is, for the photographers among you, you know about this. For those of you who are new to it, it's cool. It's called depth of field. And depth of field looks at the question of, okay, I've got some depth in space that's exactly in focus. How much does focus change as we get a little bit off of that distance, right? So if I move a little bit off of the point that's precisely in focus, how much does the focus change? And what that's controlled by actually is the aperture. And the reason is, you can see here, so here we have a wide aperture. And with a wide aperture, these rays diverge quite a bit. If my film plane, instead of being here, okay, was actually here, okay, the rays from this point would have been spread out a lot, so it would have been out of focus a lot. But on this smaller aperture, okay, where things were supposed to be in focus here, if I actually am off by a little bit there, that is, that my film plane has moved a little bit, you see that the spread is much less. And that's why the depth of field is much better. That's illustrated here. These are some pictures from Wikipedia. So here's a picture of a flower. You'll notice the flower itself is beautiful and sharp, and the background is totally out of focus. Now, it says f/5.6. Now, this is f for aperture, not f for focal length. I apologize, those of you who buy lenses, you'll buy a 50 millimeter lens, f1.4. The f is about the aperture. It means the smallest aperture, the largest aperture it can get. Also, f's are inverted. The bigger the number, the tighter the value. So 5.6 is a relatively larger aperture compared to, say, f32. So here, same flower taken from the same position, but you'll notice now that the background is in sharp focus. So if you're a photographer and you want to separate out your foreground from your background, you want to have a wide open aperture. If you're trying to look at a landscape and you want to see everything in focus, you want a very tight aperture. Here's a very nice example of depth of field. The focal plane obviously is somewhere in the middle of the phone, so the stuff that's in front and the stuff that's in back is out of focus. Another property of our imaging systems is field of view, sometimes called zoom, which is probably not quite right, but it's this idea of how wide of a view do we have. And I'm going to show you this in a lens that can change its focal length to show you that the field of view is a function of the focal length. There are lenses that can change their field of view while staying in constant focus are called zoom lenses. There are some lenses that you can change their focal length, but you have to refocus. Those are actually called variable focal length lenses. That's just the nomenclature. Here we start off with a very wide angle shot. It says 17 millimeters. And you see this little circle up there that's on that boat? As we step through and we increase from 17 millimeter to 28 to 50 to 85, what we're doing is we're increasing the focal length of the lens. Here we are at 135, 300, 500, and that's 1,000 millimeters. So we've gone from a focal length of 17 millimeters to 1,000 millimeters. That's a ratio of greater than 50 to 1. And there's that guy on the boat, right? Same boat back here. All right, there he is. Okay, so that's incredible zooming. So you think they used a tripod? Well, of course they did, right? In fact, this is something you might think about if you haven't thought, right? Let's assume for a moment that your hands shake just a little and they cause a small amount of angular deflection. Well, if my image is looking at something this wide, then a small amount of angular deflection doesn't move my pixels very much. But suppose my angle of view is, a degree or just a couple degrees, well, then a small amount of angular shift of my hands is going to move the pixels a lot. And that's why the longer the focal length, the more you have to stabilize your image, and that's why for really nice zoomed out lenses you have to have a tripod. It's not just because they're heavy, it's because you need to have things be perfectly still. Now we can compute the field of view, and the field of view actually depends upon two things. One, we already know, right? We know that it depends upon the focal length. But it's also going to be a function of sort of how big is the light-sensitive element. So here, calling D the size of the retina, okay? So the retina is the thing in the back of your eye that's sensitive to light. Just think of it as the light-sensitive medium. So D is this whole size, okay? Here's F, our focal length. And clearly, sort of half of D over F, well, the angle who's the arctan of that, the angle that's the tangent, that's going to be this angle phi here, which is half the field of view. So basically, the bottom line is the longer the focal length, the smaller the field of view. The bigger the imaging surface, the bigger the field of view. In fact, what's sometimes called medium format photography, instead of using tiny little sensors, they use much bigger sensors, so they can put still a lot of pixels but over a much bigger area. That gives them much wider fields of view.
Let's say you're at an art gallery. You've been staring at a painting that you really like, and now you want to take a picture of it. Your camera has a lens and a sensor inside. Now when clicking the picture, you obviously want the painting to be in focus. But say you also want it framed such that the picture takes up exactly the image area. That is, you want the width of the image when projected onto the sensor to match the sensor width. Let's assume that your camera lens has a fixed focal length of 50 millimeters. Your sensor width, denoted by D, is 35 millimeters, and the width of the painting, W, is 0.7 meters. Now with your knowledge about field of view, can you figure out how far the lens needs to be from the painting and how far the image plane needs to be from the lens to capture the desired image in focus? Be mindful of units when calculating your answers. In order to solve this problem, first notice that we have two unknowns, z and z prime. What does that indicate? Well, we probably need two equations to solve. One is our by now familiar thin lens equation. That is 1 over z plus 1 over z prime equals 1 over f. Let us simplify this so that we can express one variable in terms of the other. Adding the two terms on the left-hand side and then cross-multiplying. Now say we want all the z's on one side. Take z common. And finally we can write z as z prime f over z prime minus f. Remember this last result. Now we need to think about a second equation. Look at the diagram again. See anything useful? How about these two similar triangles? They tell us that half of d over z prime is equal to half of w over z. Simplifying this, we can write that is z equals w over d times z prime. This is our second result. Remember we found earlier that z equals z prime f over z prime minus f. And now we saw that z equals w over d times z prime. Equating these two and solving further, we have z prime equals df by w plus f. Now put in the value of d, f, and w here. You should get z prime equals 52.5 millimeters. Putting that here should give you z equals 1.05 meters.
So here's something cool that's related to the mathematics of photography, which we'll do more of. And it's that zooming and moving are not the same thing, right? So some people think, oh, if I zoom in, it's just like getting closer to something. Well, it's not true. Here are two pictures of the same car, okay? And you can tell already that they look somehow different, even though it's the same car and the car is in the same place. And the reason that they're different is that on the left, the car was taken with a very large field of view. So that's a very small focal length. So that means the photographer had to get close to the car. Okay? The image on the right was taken with a small field of view, a larger focal length, so the photographer had to back away from the car. So even though that the car is the same size in the image, you'll notice right away that the shape seems quite different. All right? The one on the left seems to have a lot of what's called perspective distortion. And it's not really distortion at all. It's just the effect of perspective. And that's why I said we're going to do the mathematics of that. Really not today. We're going to do that in the next one. This has dramatic effects on taking pictures of people as well. So here is a example, again, taken from the web. The website in there, it says StephenEastwood.com, where it has tutorials on lens perspective. What we have here is pictures of the same woman, but over here it's a 350 millimeter lens, standing very far away, zoomed in. Here is a 19 millimeter lens, standing much closer in order to be able to get the same size face. And you'll notice that you get this incredible apparent change of the shape of her face. And over here that's referred to again as perspective distortion, but that's not really a correct word, it's just the effect of perspective. This is why photographers use particular lenses for portrait work, and they tend to pick a lens that lets them stand what they call a normal distance away. It turns out when you and I think about what a picture of somebody should look like, we tend to think of what it looks like standing somewhere around 6, 7, 8 feet away. Or maybe a little bit further, but certainly not closer. And that's why they pick the particular lenses that they do. Here's another example of what's called the effect of focal length on perspective, and here it's being called correct perspective effect. And this is a image out of the Zisserman and Hartley book. They're actually talking about the effect of perspective and weak perspective. We'll talk about that actually next lecture. But here are two pictures of the same building. Again, one taken with a much wider field of view lens, so the one on the left, so you see this effect as the object gets smaller away, and with a telephoto lens where the image on the right, you don't see any converging of the lines. And we'll talk about the mathematics of that next time. There's a really cool thing you can do about this, and that's something called a dolly zoom. And this was an effect that I think, at least I've been told, was invented by Alfred Hitchcock. Basically, if you move closer and closer to something, but you widen out the lens as you do the same at the same time, you'll cause the object and subject in the middle to sort of stay about the same size and to be stationary. But it's going to be very weird, because what's going to happen is that all this stuff from the outside is going to look like it grows. And in the slides and study guide on YouTube is a link to the original. And there's also another link put out by somebody who wanted to just demonstrate this effect, and they did it for even a longer time, and you can get to see that. All right, our last bit is I have to break it to you that reality can be a problem. That's a nicer way of saying life sucks. In reality, lenses aren't really thin. Lenses aren't perfect. Photographers aren't perfect, except some of us. Sensing arrays aren't perfect. So sometimes we have to do stuff to try to fix these things. So here's an example of a problem that's fixable easily in mathematics and geometry. And this is referred to as geometric distortion. So on the left here, we have a nice regular grid, but sometimes our lenses are not perfect, and they'll bow things out like this, and this is called pincushion distortion. And sometimes they'll bow things out like that, and that's referred to as barrel distortion. By the way, for those of you that use Photoshop or other more sophisticated image manipulation tools, you can correct for this in the image. And in fact, in Photoshop and in Camera Raw, if it knows the camera and lens that you're using, you tell it correct for the geometric aberrations, and it will go ahead and just fix that for you because it knows about the lens and it knows about the camera. By the way, I use the word aberration. That's what we tend to use for any sorts of problems that are in how the images are created. Here's an example of the correcting of that radial distortions, radial coming out from the middle. Picture on the left taken with a lens that's actually designed to try to capture as much of the scene as possible, but it's very distorted. On the right, you can see the recovery, making it as if everything were perfectly flat. Another kind of aberration or problem in computational photography is what's called chromatic aberration. Oh, sure, if any of you are Pink Floyd fans, you're familiar with a picture that shows white light coming through a prism, spreading out and making a rainbow. I would show it to you, but I'm sure I'd have to pay Pink Floyd money. All right? And the problem is that different colored lights are diffracted different amounts by a particular lens or a particular medium. So the problem is, how do I get all the light coming from a point to land on the same place in my image? And this is shown here where they're showing you the red and blue lights as converging to different places. And here's an example at a corner, and when you blow it up, you can see this red line that's between the blue sky and the white building. Where did that red line come from? There's no red there. Well, that's chromatic aberration. By the way, Photoshop knows how to take care of that too. That one's a little bit more of an approximation, but you can remove the chromatic aberration of your lenses that way. Last one we'll talk about is what's called vignetting. If you use certain cameras at certain aperture settings, not all of the rays that are hitting from, say, the middle of the image, coming through the middle, are being caught at the corners. So here we have a lens imaging system, and we're going to talk about that in just a minute. And we've got some point, and the ones that would be near the edges, because it goes through a couple different lenses, only some of them hit the imaging medium. And so what that causes is that you get these dark areas around the edges, and that's called vignetting. The question is, what do you do about these effects? And the answer is you spend money. What I'm showing you here, and I'm assuming I can show this to you because you can just go and get it. It comes directly from the literature. There's a beautiful lens, a Nikon 24-70 zoom. Now you know that I don't own Canon equipment. Well, actually, I own some Canon. I own some equipment of every brand out there. Well, any brand that has a lawyer, I own some of your equipment, okay? Here's showing you the elements that are in this zoom lens. And you'll notice it's not just one thin lens that's moved in and out. It's made up of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 pieces of glass that are moved in different ways depending upon whether you're changing the zoom length or you're changing the distance in focus. These days, it's a combination of computer design plus knowledge on the parts of optic engineers about how to do this. And what this does is it helps reduce vignetting, chromatic aberration, geometric distortion, and other kinds of perturbations to a perfect pinhole image that we'd like to see. So that ends this lesson. Gives you a little bit of discussion about how images are formed. This is reality, but in general, lenses are designed to make it look like as if you had a perfect pinhole that happened to give you really bright pictures that were very clear. That's really good for us because the mathematics of a pinhole camera are very well understood and are very clean. They're a little bit, shall we say, complicated than simple algebra, but they're very easy to model. So when we do the mathematics of how images relate to the geometry of the world, we'll use the pinhole model. But everything that I showed you here is how we build lenses that give us this illusion of having a very powerful pinhole imaging system. See you next time. All right, welcome to Computer Vision. We're going to talk today about perspective imaging. Before we talked about sort of different geometry and configuration of cameras. Today, what we're going to do is we're going to do the math behind that. In particular, even though we talked about all these different problems and different ways lenses work, etc. Today we're going to sort of retreat to the pinhole model, sort of take the academic route of take a simplified model. So we're not going to talk about things like focus or other non-pinhole effects. Remember, pinhole camera, all the rays are in focus. At some point we might talk about fixing lens distortion, which is something you don't get in a real pinhole camera. But the reason we're doing that is to try to make our images be more like they were generated from just some really uber pinhole camera. So fundamental to our notion of imaging is our projection operation. And today we're going to talk about modeling the projection. So first we're going to talk a little bit about the coordinate system. What we'll see here is the coordinate system we're using for our pinhole approximation. The first thing is that we're going to put the optical center of projection at the origin. So here's our little COP, center of projection, and that's also going to be the origin of our camera coordinate system. Also, with our center of projection at the origin, we're going to use a standard XY coordinate system for the stuff we're going to show here. So now we're back in the land of mathematics. So X and Y are like regular X, Y, Z. So X will go to the right and Y is going to go up. Later, when you convert this to images, you're going to have to worry about making that flip. Now, here's something a little strange. We're going to, as we were talking about before in cameras, normally light comes in, goes through the focal point of the lens, and then hits the image plane. But in our mathematics here, what we're going to do is we're going to put the image plane here in front of the coordinate system, as if the light sort of magically knows how to pass through the image and hit the coordinate system in just the right place. So why do we do this? Well, because it's mathematically convenient, because this way our images don't get inverted. Y stays up. All right, before we had to worry about things being switched left and right and up and down. Well, now X stays to the right, Y stays up, and we don't really build a camera with the image plane in the front. We put the image plane behind, and then we have to rotate things back to get Y up and X to the right. So for the math here, we're going to put the image plane on the right. Now, one of the implications of this XY coordinate system, in order for this to remain a right-handed coordinate system, so you remember X, Y, that this way is Z. What it means is that Z is now pointing in from the camera, not out to the world. So here's Z pointing this way, all right? Sometimes this matters, sometimes this doesn't. You see here we wrote down that the world's position of some point was X, Y, and Z, and we didn't say negative Z. Well, that's because it's a Z value, which could be negative 20. And we can go back and forth on this, but basically, in order to keep a right-handed coordinate system and everything sort of not have to worry too much about how we do the matrix multiplication and stuff like that, we have that Z goes negative the further away that you get. So what's going on here? So what we have here, we have our world point here. All right, so here's our point in the world. And the ray projects down to the center of projection. Normally our image plane would be back here, but we're going to say, so the idea is that that ray intersects the image plane at this point, which we're going to call X prime, Y prime, and it's written as minus D, because the idea is that the distance, like the focal length distance, the distance D from the origin to the image plane, that's a positive distance. So what that means is that the location of this point is going to be X prime, Y prime minus D. Using this projection from the world point to that image plane, we get projection equations. And we can compute the intersection, that is where X prime, Y prime is, by looking at similar triangles. Kind of just like we did for the thin lens. So basically this triangle and the projection triangle here, these are similar triangles. And by the similar triangles, basically we get that the XYZ location, the location of the point, is now mapped to this point here, which by similar triangles is minus D X over Z, minus D Y over Z, and minus D. And here you can see that negative D issue, right? So basically what it says is that X is divided by Z and multiplied by D, by whatever that essentially focal length scale factor is going to be. So using that similar triangle and knowing what the location of that point on the image plane is, well, the question is, what is the location in the image of that point? Well, to get the location of the image, we just throw out the last coordinate, and basically it says, not basically, exactly, it says that X prime, Y prime, which is the XY location in the image, is just minus D X over Z minus D Y over Z. Normally in class I'd say, so any questions? But Megan understands everything totally, and you guys are all brilliant, so I'm not going to worry about it. By the way, one of the obvious implications of this dividing by z is what? Well, it's that objects further away are smaller in the image, which is something we all know anyway, right? Take an object, pull it further away, and its size in the image gets smaller. And that's because you're doing perspective projection, and the points are mapped to the values that are proportional to x over z and y over z. As z gets bigger, x and y get smaller, with respect to 0, which we're putting at the center of the image. Do you hear that? 0 is at the center of the image under this, so not at the top left-hand corner. So we may have to worry about that later, too. Time for a little quiz. So when objects are really very, very far away, the real x, that is how far off from the center they could be, might be huge, as the real z. Could be miles. So if I move the camera, the origin, those numbers hardly change, right? The location of the real x out in the world, the real y out in the world with respect to this point, if it's miles away, if I move this a few inches, nothing actually changes very much. So this explains which of the following. A, why the moon follows you. I hope the moon does follow you. It follows me, but maybe I'm special. Why the North Star is always north. That's B. C, why you can tell the time from the sun regardless of where you are. And D, all of the above. Well, the answer here is clearly D. And the reason is that basically when I move my camera, since essentially capital X, capital Z don't change, right? Where the point of the moon lands on my image plane, it doesn't change either. Now, it'll change if I rotate, of course, but we're just talking about translating. Now, pretty soon I'll translate right out of the field of view, and Megan's going to get unhappy, so I'm going to come back here. But if you've ever been driving along and you see the moon and it just sort of follows you, okay, that's because the X and Z, well, the Z's not changing at all if I'm going this way, and the X is changing maybe by miles, okay? But the moon is, what is it? It's like 200, I don't know, it's really, really far away. Somebody look up I think it's 250,000 miles, something like that. Anyway, a lot shorter than the distance between here and Roswell. So as I go all the way from here to Roswell, the X hardly changes, the Z hardly changes, so where it appears on my image doesn't change. And basically, this is why things that are very far away don't move as I move. The only thing that matters are the angles. So this is true for the sun or the North Star, these kinds of things, and it's because of this perspective projection. Now we get to the ugly stuff, homogeneous coordinates. It's not ugly, it's beautiful for some twisted notion of aesthetic. So that operation where we take x over z and y over z, is that a linear transformation? Well, the answer is no. Now, before we said that, well, division's a linear operation. Sure, division by some constant, by a, 1 over a, multiplying 1 over a, that's a linear operation. But here, and I take x, y, and z, okay, I actually have to pull out that z and divide the x and the y by it. And so if I've got another point with x1, y1, z1, I divide by that z. So it's not a linear operation. I have to essentially change what's going on. So what we're going to do is we're going to do a trick. And the trick is we're going to add one more coordinate, all right? And we can do this in either 2 dimensions or 3 dimensions. In 2 dimensions, xy becomes xy1, xyz becomes xyz1. And this bottom coordinate, which right now here is written as a 1, later it'll take other values, that's the homogeneous addition, the homogeneous coordinate. Sometimes it's called a scale factor, but I think that's inappropriate. It should just be viewed as the homogeneous coordinate, or the homogeneous component of the vector. So converting from regular coordinates to homogeneous and back again is pretty easy, right? If I have the homogeneous coordinate xyw, I get the non-homogeneous by just dividing by w. So in 2D, x over w, in 3D, x, y, and z, each over w. So now you see why converting xy1 to non-homogeneous, I still get back the x and the y as I had before, but if that last homogeneous coordinate is not 1, then I'll get a different value. And by the way, this makes homogeneous coordinates invariant under scale. If I were to multiply the entire homogeneous coordinate by some constant, say a, so I have ax, ay, aw, when I do the conversion back again, doing the division, the a just cancels out. So the really cool thing about doing this is that now we can take perspective projection and make it a linear matrix operation while we're working in homogeneous coordinates. And we don't have to worry about the non-homogeneous part until the very end. So that looks like this. So here I have a 3 by 4 matrix, and you notice it's 1, 1, 1 over f. And I multiply that by my homogeneous 3D coordinate, x, y, z, 1, and I get out this three-dimensional homogeneous coordinate, right? So it's a 2D homogeneous coordinate 3 with component x, y, and z over f, okay? And I can just keep this around as a homogeneous coordinate until I actually need to use it in an image. And when I use it as an image, I do the division of the top element by the homogeneous element, and I would get f times x over z and f times y over z, which, by the way, is sometimes called uv, and those are the coordinates in the image of some point x, y, z out in the world projected through a projection with a focal length of f. And so our projection operator was this linear matrix multiplication, and as we know, we all love linear matrix multiplications because we know how to do them a lot and invert them and all other kinds of stuff. And it's really the basis behind projective geometry and the projective mathematics that we'll be using for a bunch of this course, actually. By the way, f from now on is for focal length. Before we were talking about that distance d, so here our focal length is the distance from the center of projection to the image plane. And it is not the f of the aperture that we were talking about last time. I probably shouldn't even reminded you because it was probably months ago since you watched that lecture. But f here is always going to be focal length, which is the distance from the center of projection to the image plane. So how does scaling the projection matrix change the transformation? Well, here what I've done is I've scaled my projection matrix by f. I could have scaled it by something else, but I'll scale it by f. So now, instead of having along that diagonal of 1, 1, and 1 over f, instead I just multiply by f, and I have f, f, and 1. Multiply that by my three-dimensional homogeneous coordinate vector, which has 4 dimensions to it. Now I get out fx, fy, and z. And then when I do that division, what do I get? The same thing I got before. Okay, so it was invariant.
Try writing some code to project a point from 3D to 2D. Make sure you use the matrix operation just described. Let's say you're given the coordinates of a point P and a focal length f. Write a function that returns the location of the projected point on the 2D image plane. Here's what your function should look like. You can test your code by passing in a value for P and f. Let's say the units are millimeters. You can display the result using disp. Try out different coordinates and focal lengths. Note that we will test your function against a known set of inputs when you hit submit. So the first thing to do is define your projection matrix. Note that it has a size of 3 cross 4. That is 3 rows, 4 columns. Next, we convert P to homogeneous coordinates and transpose it. The resulting size should be 4 cross 1. That is a column vector with 4 rows. It is easy to append an element to any vector. A single quote after a vector transposes it. Finally, we can apply the projection transformation. And this ends up being a simple matrix multiplication. Note that we use star, not dot star, because we're not doing element-wise multiplication. Remember to convert back to non-homogeneous coordinates when returning the value. U equals x by z, and v equals y by z. And that's it. Here's a quick check to see if the function's return values make sense. Say we keep the focal length at 50 millimeters. Then we know that any point at 50 millimeters should be projected at the same xy coordinates. Let's try this out. This should be true regardless of what the coordinates are. Let's try something else. Similarly, points at double the focal length should be reduced to half the size. See, perspective projection is not too bad.
All right, let's just talk quickly about a couple of the geometric properties of perspective projection. What this figure is trying to show is a few things. The first of all is that points go to points. So that seems pretty clear. I have some point out here, and I'm going to put that point sort of out on my ground plane, right? So here's my center of projection O. I'm looking at some point on the plane, and here's that point in the image, right? Because it's just the single ray that moves through. Something else that's true in perspective projection is that line, so here's a line here, project. So one way of thinking about it is, here's my origin. Think about it going through here and coming through there, and it sweeps out this whole plane, and that plane intersects the plane made by that line on the ground and the point, the center projection, intersects the image plane along this line. So what that's saying is, not only do points go to points, lines go to lines. And if lines are going to go to lines and points go to points, then polygons go to what? They go to Mercury. No, polygons go to polygons. All right? Not rocket science, but it is this invariance of lines in perspective projection, lines mapping to lines, that we leverage quite a bit. A cool thing in perspective projection, and something that you already know, is that parallel lines in the world almost always meet at a point in the image. So here's an example of, that's two parallel lines out on the ground plane, and they project to two lines in the image, and you can see that they meet at this point, sometimes called the vanishing point in the image. And the canonical example of that is always railroad tracks, where the tracks themselves all converge to some point. So we can sort of intuitively think about that, but what's really cool is you can see that directly from the mathematics of it. So let's think about what a line in 3 space is. So a line in 3 space can be parameterized by a single value, a single parameter. So in this case, we're going to use t. So we have x of t, y of t, and z of t, and the idea is as t changes from maybe minus infinity to infinity, or 0 to however you want to do it, you would move along that line. And a line in 3 space starts at some point in 3 space, I'm saying here x0, y0, z0, and then it's moved along some vector. So right now we're using the vector ABC. So A in the x direction, B in the y direction, C in the z direction, scaled by the value of t. So now let's take a look at where all the points on the line lie in the image plane. All right, so that's for every x, y, z, what's the x prime and y prime for the given t? Well, we learned that the equation of the projection from x, y, z to x prime is just fx over z, and for y it's just fy over z. So here we just substituted in the expressions from the other side in terms of t. So that's where all the points on the line go. But what happens as t gets really big? In the limit, as t goes to infinity, and I'm going to assume for now that c is not 0. We'll talk about that in a minute. Okay? The limit of x prime is just fa over c. The limit of y prime is just fb over c. What's missing? What's missing is x0, y0, z0. In other words, it doesn't matter which point in the world this line starts from. I could start from here, I can start from here, I can start from here. As long as the points are all moving in the direction ABC, they're all going to converge at this point in the image. And that's why it's the case that all parallel lines in the world, so lines that are parallel in the world, will all converge to a single point. So the railroad tracks and a fence along the railroad tracks, since they're all parallel in the same direction, they all converge to the same point. So what does it mean that c is 0? So c is 0 means that the z value doesn't change. So assuming I'm holding my camera like this, so my image plane is a vertical plane, so that z is perpendicular. If the z value doesn't change, it means the line in the world is parallel to my image plane. Doesn't get further away or closer, it stays parallel. And those lines will all stay parallel lines. And that's why I said that almost all pairs of parallel lines in the world converge to a point. If you have parallel lines that are vertical or aligned with the image plane, they don't converge. These points are called vanishing points. Here it's demonstrated that each set of parallel lines, that means they're all in the same direction, meet at the different point. Another thing that's true is that parallel lines that are all on the same plane, they all converge to collinear vanishing points. And you know this as the horizon. So here is one set of parallel lines in the world, and they converge to a point here. This is another set of parallel lines, and they converge to a point there. If I had parallel lines going away from the camera, they would converge like this. All right? And the horizon is this line right there. And that's because all of those parallel lines that I drew, they're all in the ground plane. So they all converge at vanishing points on the horizon. By the way, it turns out getting the vanishing points consistent when you're putting together an image, like you're taking a piece of a building here and putting something else together there as opposed to actually taking a picture, is actually kind of hard. So if you want to try to find a fake image, that is something that's been photoshopped, put together, go to your local supermarket tabloid, you can often find pictures where the vanishing points don't seem to do the right thing, and that's because it was made up of parts of an image that weren't taken with a camera aligned with those parallel lines all in the same way. A little bit more, maybe some of you actually took an art class before you decided to lose your soul and become an engineer. And maybe they taught you about three-point perspective. Well, and here's a drawing of three-point perspective. And basically what they're talking about is if I've got a cube in the air, that defines three sets of parallel lines, like the left face, the right face, and then underneath. And you can see that drawn here. And that's where it comes from, is that parallel lines converge to different vanishing points. Here's another example. I think this is a Zisserman product. I'm not sure. So just a really quaint old building. And there's vanishing point from the right, from the parallel lines there, another vanishing point on the left, and without talking about others, you can see where the horizon is, okay, right across there. That's where all the lines, for example, on the ground would converge. We're very sensitive to this structure of parallel lines and what they convey to us. Now, most of you have seen this Mueller-Lyer illusion, right, of which one of these lines is longer. And you probably all know that, well, actually, they're the same length. And you probably saw that back in grade school. It's kind of cool. Let me show you another version of it that shows you why this can be an interesting effect. Okay, so here we have a picture, okay, and you can see the red arrow in here and the same red arrow in there. Let me take that away. And now the question is, which of those is longer? And that one's a lot harder for you to say that, you know what, they're actually the same length. So you go back there. In fact, even when I pull them away, when I stare at them, they look like they're different lengths, but of course they're actually the length. And that's because you're using this perspective projection as a way of saying that in the real world, okay, the distance from here to here is more than the distance from here to there, actually, right? That is, this is the height of the whole wall, this is just the height of the ticket window. So it looks the same on your image, but your brain automatically wants to undo that projection transformation. All right, little quiz. What determines at what point or which point in the image parallel lines intersect? A, the direction of the lines in the world. B, whether the world lines are on the ground plane. C, the orientation of the camera, and D, A and C. So this one's probably bugging you just a little bit, so let's just go through them, all right? Let's talk about A. All right, well, of course A has got to be true. The direction of the lines in the world, of course, we just showed, the math shows that, you know, where they intersect in the image comes from there. And then it says whether the world lines are on the ground plane. Well, all world lines that are on the ground plane all intersect, parallel lines, they all intersect at what? They intersect at that horizon. But now here's where it was a trick question. I said, what determines at what point in the image parallel lines intersect? I didn't say on what line, it's at what point. So that's why B is not true. Now C is the orientation of the camera. So you can think about this two ways. One, everybody knows that where a point lands in your image has something to do with where you point the camera. Watch Megan's nose move. Okay? Yeah, as I move the camera, of course things move. The right way of thinking about this is, remember that ABC, which was the direction of the lines in the world? But that's in some coordinate system, and that coordinate system is defined by our camera's center of projection. That's the XYZ center of our universe there, and we're defining all of our points in that coordinate system. And that's why it's A and C. All right, so to finish up the lesson, besides perspective projection, there are other types of projection operators, which in fact are sort of special cases, and they're used sometimes, so they're worth mentioning here. One interesting form of special case of perspective projection is called orthographic. And as it's drawn here, basically orthographic is when I take my world and I just smash it right into my image plane. And what's interesting about that is it actually can be thought of as a special case of perspective projection, but where the distance from the center of projection to the image plane is infinite and my object is infinite. Right? If those both were sort of infinite, then basically what I end up doing is the z value doesn't matter because those rays are parallel. So that's why this is also called parallel projection. And so xyz just gets moved to xy. This is actually sometimes used as a model for a telephoto lens, because telephoto lenses are looking at things very, very far away. So all of your rays are almost exactly parallel. Now, of course, it has to be scaled. And so you end up scaling the x and scaling the y, but it's the same scale value for your whole world. I mentioned that because we're going to talk about something called weak perspective in a minute. So basically, when you throw away the z value and then you just scale the x and y by some number, that's this parallel projection. And since I said it was a special case of perspective projection, there must be a matrix operation that would recover it, and here it is. And you'll notice now that this value is 0, okay? And this value is 1. So xyz1, the matrix just equals xy1, and when you divide out by the 1, you just get the xy. So even this orthographic projection can be represented as the same matrix, as a matrix multiplication when we use homogeneous coordinates. Another model is called weak perspective, sometimes called scaled orthographic, but that's a bad choice. There's also something called paraperspective, but what we're going to call weak perspective is the following. The idea is that we know that when things get further away, they're going to get smaller. But what we're going to do is we're going to say that all the points on a given object, we're going to assume they're all at some constant depth. We'll say z0 as is written here. Okay? So for all the points on that object, x, y, z will get mapped to fx over z0, fy over z0. So that object will get scaled. But some other object, might be a significantly closer object, it will get scaled by a different value. So basically, in weak perspective, what we're saying is that the difference in depth over an object, or over the range of an object, is very small compared to the distance in depth from the object to the center of projection. And if that's true, then you can basically say that each object has its own scale factor. Of course, as a special case of perspective projection, we can do this in a matrix form also. So here we have the equation or the transformation we said before. xyz goes to fx over z0, fy over z0. So basically, f over z0 is acting like a scale factor. Okay? So here we have our projection matrix, which now, instead of having a 1 over here, has a 1 over s. And then when I multiply that through on the homogeneous coordinates and then divide, I'm dividing by the 1 over s, which gives me sx comma sy. So weak perspective gives you this scaled effect of each collection of points that sit on a given object. So those are the three camera projections that we'll talk about. The one that we'll use all the time is perspective, which ends up giving you fx over z, fy over z, and we showed you how to do it in matrix coordinates using homogeneous coordinate system. And then we also talked about weak perspective, where you have a scale factor sort of per object, or orthographic, where you basically just throw away the z value. All right, so that ends this lesson on projection. We're going to use the perspective projection a lot, so get to know and love it. And by the way more math is coming, so fasten your seatbelts.
Anamorphic images are ones that require the viewer to look from a particular viewpoint to show the desired visual. Other perspectives usually yield a stretched or distorted result. Artists use their knowledge about perspective projection to create some amazing illusions, like this Lego army designed by Leon Kier. Viewed from any other angle, it looks strange. This art activity popularized by Myrna Hoffman uses a curved mirror to undistort a flat drawing. Can you find other cunning examples of people hacking perspective projection? Share with your peers on the discussion forum. I encourage you to create your own. It's a lot of fun. Check out this excellent Instructable from Mr. Grease Tattoo for some inspiration.
Hello, welcome back to Computer Vision. Today we're going to start talking about stereo, and this particular lecture is on stereo geometry. In general, the next few lectures are going to be on the relationship between sort of camera geometry and scene geometry. We're starting with stereo because, frankly, you guys are going to do this in a problem set, and I want to be able to get you there quickly. And also, in some sense, it is the conceptually easiest way to get started. So stereo is really just a special case of having multiple views of an image. two particular views. And here's just an example of two views of a vase. In fact, we're going to get to this particular figure a little bit later when we talk about epipolar geometry. But the idea is that there's this relationship between two views, and you can use it to recover the depth that's there. We'll also take a look at sort of having arbitrary different views. This is an image that comes from work on using special features to align objects and be able to detect that they're there. But again, you have two different views and you have to figure out how they relate. This is an example of what you can get from stereo. So the picture on the left is one half of a stereo pair. On the right is a crude depth map. The brighter things are, the closer they are. In fact, we're going to talk about how to compute exactly that. And in general, you can have lots of views where you have images taken from a whole bunch of places or a whole bunch of directions, and it's a question of how do these images relate. And this notion of how images relate and how do they relate to the scene, that's what we're going to be focusing on. So the first question to ask is, well, why multiple views? Obviously, structure and depth are fundamentally inherently ambiguous from a single view. Remember, we're projecting from 3D to 2D. When we do that, we lose information. So here's an example of a man pushing the Leaning Tower of Pisa over to make it lean even further, and either he's very large, the building's very small, or there's an ambiguity when you project from 3D to 2D. Or how about, so those of us who grew up in the States were a fan of It's a Great Pumpkin, Charlie Brown. So that might be a picture that looks like this, which would be really a great pumpkin. But of course, what's really going on here is that the location of the camera makes it such that this picture just appears like the pumpkin is very large. You know, what's the fundamental problem? Well, the fundamental problem comes from perspective projection. Here we have an optical center, all right, and we have several points, such as P1 and P2, projecting along the same ray. And of course, because they project along the same ray, they land in the same spot, P1 prime, P2 prime. And so that's where the ambiguity comes from. And the question is how to figure out where P1 and P2 really are. And the trick, of course, is going to be to look at a different camera.
When you look at an image, what properties indicate differences in depth or provide hints about an object's shape? Think about various features that convey structural information in a scene. Stereo is not the only thing at work. After all, you are seeing these images on a flat display. Type in depth and shape cues you found as a comma-separated list. Feel free to look at other images or just around yourself for ideas. Some depth and shape cues I could think of are shadows, texture, focus or blur, parallel or converging lines, lighting, shading, objects occluding each other, and size and scale of objects.
So before we do think about how we're going to do this in machine, what about humans? How do humans see in 3D? All right. And frankly, we can actually do this using just one eye before we even get to two eyes, because we look at these different cues. So here's an example. So when you look at this picture, in fact, when you look at any flat picture on a piece of paper or on a single screen, there is only flat real depth, and yet you see the depth that was in the scene. So here we have perspective effects. You assume that those houses are all the same size and that they're fading off into the distance is what makes them smaller. So you perceive depth from this perspective effect. Shading, here's a picture on the left, and B and C are some of the recovery of using an automatic method to try to recover the depth, and it's using just the shading information. You assume that the skin has a particular type of reflectance, and your brain figures out the depth in it. By the way, this is why certain kinds of makeup is used, right? By changing the shading on the cheeks, you change the apparent shape of the face. Even though, of course, you didn't change the face, you just changed the reflection. Texture. Here you see a wall, and you can tell that the wall is sort of curving around, and that's because the texture elements on it are changing. Those circles with the little lines on them, that's an early attempt at being able to recover orientation from texture. A more recent piece of work done by Lowe, here you have a picture, you see the strawberry, and you see the texture, and the texture changes as the surface tips away from you. And the system actually works on trying to recover the surface height or the orientation from the change in texture. And here's a really cool one. Remember we talked about that in real lenses, there's a single focal plane of depth. That is, there's some plane out there in the world that's at depth, that's in focus on the image plane. And the more you're away from that particular location, the more out of focus you become. So you might be able to take how an image changes focus as you change the aperture. Remember, a very tiny aperture, everything's in focus, and as you open up the aperture, the depth of field shrinks. And that means that things that are further away from that focus plane get fuzzier faster. So you could actually take multiple images from that same point, change the aperture, and figure that out. So it's a little bit of a cheat, because yes, it's one eye, but it's multiple pictures. All right. Here's an image of them recovering a 3D shape and depth from defocus. And the last one, and this is something we're actually going to look at a little bit later, and in fact it's actually related to stereo, is the idea that from a single eye, if something moves, you can tell the shape. Now, here's a picture of a statue, and it's pretty hard for you to figure out the motion that you would use. Mostly you're looking at the shading. So here's a simpler example. All right. Now, if all our video gods are working right, and the web is working correctly, and you've got decent bandwidth, and the moon is in the sun with the 7th house of Jupiter, whatever that is. Anyway, you should all be seeing a rotating cylinder. Now, some are going to be seeing it rotating counterclockwise, and some are going to be seeing it rotating clockwise. And that's because you can't be sure whether the dots moving to the right are in the front of the cylinder or in the back of the cylinder. But the idea is, purely from motion, you are seeing this cylinder rotate. It's pretty amazing, actually, if you think about it. And we'll talk a little bit about structure for motion later on in the class. But the idea is, from a single image, but the thing moving, you can get depth. We're going to come back to that in a minute, because it's a single image with the thing moving. Well, we can also have two images where the thing stays the same. These general methods of estimating shape from some cue, shading, texture, focus, etc. For a long time, that was a big deal in computer vision. It was called shape from X, sort of very popular in the late 70s, early 80s, which I know is prehistoric history for most of you. But the fundamental idea was that from an image, and from some assumption about the nature of the world, like that those houses are all the same, and therefore they're probably getting further away, the brain could compute depth, and we wanted to build machines that could do that as well. But we, and a lot of other creatures, have two eyes. So that we call stereo. And in stereo, the key is that the image from one eye is just a little bit different than the image from the other eye. Here I see the right side of Megan's nose, and here I see the straight part of Megan's nose. Megan's nose is pretty straight. Mine's crooked. Anyway. So you can think of stereo as recovering the shape from the motion that's between the two different views. And the idea is to infer that 3D shape. Before talking about exactly how to do that, people have been looking at this ability of the human brain to do this for a long time. And in fact, one of the cool things that showed up was stereo photography. So Charles Wheatstone, back in the early 1800s, invented the first stereo viewer, all right, where you would take two pictures and then put them through lenses so that each eye saw a slightly different picture. All right, so what you've got here is this wooden thing that prevents the image in the left eye from being seen by the right, and likewise the image in the right eye from being seen by the left. And there are these lenses here that essentially train the eye right on the image that's right in front of them. People were fascinated by this. So here's a picture of Abraham Lincoln taken in 3D. So we went from 1838 to 1860, so just 20-some-odd years, and already you're doing 3D portraits of the President of the United States. So it became a really compelling thing for people to see, because you take this flat thing, and all of a sudden you would see depth. Here's a stereo pair of Thomas Edison, most famous inventor of his age, it says, probably true. And you could view that through a stereo viewer. Or you could do something really cool. You could make what was called anaglyph stereo. And anaglyph stereo put down sort of red and blue imagery. And what that did was, imagine if you're looking at a white piece of paper through a blue filter. Well, everything's blue. It throws away all the light except the blue, and the white has blue in it. So if you put blue stuff on there, it doesn't change anything. So basically it becomes invisible. Whereas you put a red filter in it, the blue looks very dark. Likewise, you put the red image, it becomes invisible to the red filter. And so anaglyph stereo became popular for a little while in cheap three-dimensional movies. There's a picture of those stereo viewers. And this is a great picture because it's a stereo image of kids looking at stereo pairs in the library. And this is in the early 1920s. And the thing to realize is it gave you a certain sense of realism. So people used to use it to experience faraway places and things that they couldn't see otherwise with a reality that they don't get when they just look at an image. So for example, here's this picture of this bridge in India. So all of a sudden you could feel like you were in India, which was different than just looking at a static picture. And when I grew up, lots of us had these ViewMaster discs. Okay, where you would put the discs into the little viewer and you would slide it down and you would see the two different things. And, you know, you got educational stuff. So when I was a kid, they landed on the moon and they made stereo photographs of men on the moon, which is really cool, talking about someplace you couldn't go. Or much more importantly, you could get Spider-Man, which is really good. And of course, if we had the internet then, we would have known that you could have ordered stereo porn, but we didn't know that at the time. Now you guys, you get three-dimensional television. So for you, this is hardly new and compelling at all. But it's basically the same principle of making sure that two different images are shown to each of the eyes. So here's the basic idea, all right? Two slightly different images. These are two stereo animations taken from this website listed here, where we just alternate showing you the left image and the right image. Already, if you just take a look at the fence post here, you can see that these pictures were lined up in such a way that the fence post was sort of right at the same point in the two pictures. And you can see that the stuff that's in front seems to be going that way, stuff in the back goes that way, and then back again, all right? Or you can switch them. But the idea is that stuff in front of what you're verged at moves in one direction, and the stuff behind it goes back. We'll actually see that when we talk about the ordering constraint 2 lessons from now. Here's a cool one that was done of somebody diving into a pool, and you can see he adjusted the images so that at the depth of where the swimmer is, the two images are exactly lined up. So the bubbles, the splash moves in one direction, and I love that the shadows on the bottom of the pool move in the other direction. So the basic idea is that from two different views, from how they move, you get a sense of what their depth is. So let's talk a little bit about stereo vision. How do humans do it? And at the very, very end of the course, we'll talk a little bit about the physiology of the human system, but today I just want to talk about the computation. If you think about it, you could imagine that stereo is done a couple of different ways. One way might be that you sort of find some regions in one image and then you find those regions in the other image, and your brain compares them and sees how they've shifted relative to each other, and then somehow figure out the depth. Another possibility is that maybe you just process the very low-level images doing some sort of a comparison and get the depth. So you do fusion first, and then you do recognition. So there's a question of whether you do monocular recognition and then fuse, or you fuse the images and then do binocular, that is, given the fused images, do the recognition. So back in the 60s, a psychophysicist named Bela Yulis wanted to look at this question. So to test this, he made a pair of synthetic images that were obtained by essentially spraying black dots on white objects. All right? So here's a notional description, comes from the Forsyth and Ponce book, of sort of putting, imagine that those are white, and you sprinkled pepper, you sprinkled black dots all over the whole thing, and you took one picture from this side and another picture from that side. What you'd get are these two images, okay? Now, when you look at those two images, you don't see anything in there. But if I showed them to you in stereo, which is very difficult for me to do here, you would actually see that block raised. All right? So what we can do is we can animate those, we can animate random dot stereograms in the same way that we animated the swimmer. I don't have animations of this one, but I do have animations here of this. Well, if you look at this for a little while, I hope you'll see a shark. Does everybody see the shark? Okay, so this is the the head sort of sticking out, then it bends around, and then the tail sticks out again. So you'll notice I just drew that tail, okay? But, of course, the tail is not in any individual picture. It's only in understanding the difference between them. Now, this was actually done from what's called an autostereogram website. You can go take a look. There are ways of making these so that if you can use the same picture, cross your eyes, or stare at them differently, that you'll get different images in the two eyes. But I think you get the idea that from these two images, you can see the depth. And what's interesting is if I present one to one eye and one to the other, you see that depth. So the answer to Ulish's question was whether you process the image first, finding these regions, and then line them up to do the stereo, or you first line up the sort of little local pixel area in order to do the stereo. It's clear that you do that first. You don't that you do the stereo first. You don't have to have any specific objects or region. Sort of a clean way of saying it is that human binocular fusion, fusing the two together, is not based upon matching large-scale structures or any individual process of the image. It's actually based on a low-level process that directly fuses the two images. So now let's think about the geometry of stereo and get to the mathematics. The basic idea is this. If I have two cameras, and remember cameras are defined by their optical centers, all right, and they're both looking at some scene point, if I can figure out which 2 points in the two cameras are the same point, and furthermore, if I can tell which way, if I know something about which way the cameras are pointed, then I can figure out the depth of that point. That's it. So for estimating the depth between the stereo, remember the shape between the two views, there are two things we have to consider. First is information on camera pose, and sometimes referred to as calibration. How are the cameras oriented in space with respect to each other? And the second is on image point correspondences. That is, which point corresponds to which. So here you see the red dot in the two images, left and right, are both corresponding to that front corner. What we're going to do is we're going to swap that order. We're going to talk about doing the image correspondences first, because that's what you're going to do for your problem set, and it's the fundamentals between stereo matching. And then we save calibration for later, because calibration is also used for a whole bunch of other types of geometric processing that we're going to do with the cameras. What we're going to do is we're going to step through the geometry for a pretty simple stereo system. The first thing we're going to do is assume that the optical axes are parallel. That's these right here. And because the optical axes are perpendicular to the image planes, it means the image planes are parallel. In fact, we're going to assume that they're exactly coplanar. So this image drawn here is as if we were looking down on our camera rig system, right? The cameras are looking out, okay, and this is the image plane right here, so we're looking down on the plane. And that will let us take a look at how things shift left to right in the stereo imagery. For our geometry here, we're going to assume our cameras are separated by a baseline B, and that both cameras have a focal length of f. So f is on both sides. So for the two cameras, they both have the same focal length. Now, let's assume that we have some point P in the scene, okay? And it's located at a distance z in the camera coordinate systems. Now remember, the z is the distance all the way down to the centers of projection. Okay, so that's z, not to the image plane, but to the center projection. And if you remember, just for mathematical convenience, we put the image plane in front of the center of projection so things don't get inverted. So that point P projects into both the left and the right images. Now, just to make sure you're paying attention, on the left image, the distance is going to be positive, and on the right image, the distance is going to be negative because our origins are right in the middle. 0 here is in the middle of the image plane. Got it? So distance is positive on the left and negative on the right. These quantities XL and XR are meant to be distances, so they're positive values, but whether they move plus or minus depends upon which image we're in. So here's our point PL, and there's our point PR. And PL is, as I said, this distance XL to the right of the optical axis, so it's positive. And the point PR is to the left, so it's negative XR to the left of 0. All right? So now we can do some simple geometry to figure out the relationships between x's, p's, b's, p's, and everything else that happens to be in the picture. We want to find an expression for z. So we start by using similar triangles, just like we did for projection, but these are different triangles, the ones looking down. We have the first triangle, which is based upon the point P and each of the projections. That triangle is shown in yellow. And then there's another triangle that's based upon the center of projections and the point P, and that one is shown here in blue. See how it faded in? Let me back it up. There it is. That's the other triangle. Well, we now have two similar triangles, so we can write down what the relationship is between the edges, namely that B minus these distances, so that's going to be this distance, okay, is to this distance, which is just Z minus F. That's same proportion as the total baseline B, I'll draw it here, is to the total Z. Okay, those similar triangles give us that relationship. So a very little bit of rearranging gives us an expression for Z that says that Z is equal to F times B over XL minus XR. Okay, and that difference between the left and the right amount, that's called the disparity. The cool thing here is that we're computing the distance in the scene based upon a difference between these two. Now, you should ask yourself a little question here. What happens when disparity is 0? Well, when disparity is 0, that means that some point in the scene projected to the same point in the left image as the right image. In other words, as I moved from my left to my right camera, that point didn't appear to move. Well, remember we had a quiz on this. We talked about how come the moon follows you. Well, the moon follows you because Z is so far away that you get no change in the left and the right. So the disparity is 0, so the depth is what? It's infinite. Okay? And that's the inverse relationship between disparity and depth.
Say I have two images from a stereo setup. One in which I have a tree on the right-hand side and a person standing in front of it a bit to the left. Stereo images are not very different. In the second image, I have the same tree, but the relative position of the person is a little different. Can you figure out which is the left image and which is the right image? Enter the word left or right in the corresponding box below each image. Here the left one is the left image and the right one's the right image. From the left image, we know that the person is standing in front of the tree. Now if you imagine the two stereo cameras, then you'll notice that the left camera is viewing the scene from a little bit to the left, vice versa for the right camera. Similarly, if we look at the right image and consider the two stereo cameras, same thing here. Now if we know that the person is standing in front of the tree, then the only combination that makes sense is that the left image is from the left camera and the right image is from the right camera. One way to think about it is the following. If you shift your viewpoint to the right, then objects that are closer will move further to the left than objects that are further away.
So here we're going to show you some example of disparity, okay? In the left-hand side, you'll see that there is a point at the bottom of this window, okay? And in this image on the right over here, and by the way, it took me a while to figure out which image was left and which image is right, and I did that by looking right up here at the trees. You can see that in the image on the right, the chimney has moved to the left with respect to the tree behind it, so that's the right image. What happened is if I go to the same location in this image as in the first image, I don't land on the window. I actually have to move this far in order to get to that window point. That's the disparity. And in fact, you can build what's called a disparity map. For every point x, y, you can say, what's the disparity? And you'll notice something about this disparity image, right? Notice that the stuff here is brighter than the stuff there. Well, I just made an image of disparity. And remember, disparity is inversely proportional to depth. So the brighter values are the closer z's. All right? And the smaller values are further away. And the really small values, which are very dark, are going to be further away yet. Okay? And that's this notion of, from disparity, being able to get to depth.
So you saw how stereo cameras and photographs have been around for a while. Today, stereo plays an important role in entertainment. Have you come across any innovative uses of stereo? Especially something that relates to computer vision? Enter your response in the box to the right. You can enter multiple examples, one on each line. Thank you for your response. I hope you found some examples that involve estimating depth from stereo images, or perhaps novel ways of projecting stereo images so that it's easier to see three-dimensional shapes. I encourage you to share and discuss your examples on the forum.
That ends the lesson on stereo geometry. The idea is that if you have calibrated cameras, if you know the match, then you could compute the depth. So this has been sort of general. The only math that we did was the relationship between disparity and depth. In the next lesson, what we'll do is we'll focus on actually finding the disparity, figuring out which point in one image matches which point in the other image. And that's what you're going to be doing in your problem set. Then we're going to work on calibration, which is determining the relative views. And by the way, you're going to do that in a different problem set. But we're going to break these down one at a time. That's it. Welcome back to Computer Vision. This is going to be the second in a series about stereo. In particular, we're going to focus on what's called epipolar geometry. We had said last time that if we had two images and we knew something about the cameras, if we could find correspondences, given that known relationship, we could find the depth. And we talked about disparity. And disparity was the idea that the location of a point in an image would change depending upon the depth of the scene as I moved my camera. And if I actually had the disparity, I could make a disparity map which tells me how all the points have shifted, and disparity was inversely proportional to the depth, and that's what this disparity map on the right is. But how do we find the disparity? Essentially, given one point in the image, we need to search for it in the other. But our intuition tells us if I know something about how the two cameras are aligned, if you give me one point in the picture on the left, it can't be anywhere on the picture on the right. It has to be somehow constrained in terms of where it can be on the left. This lesson is going to be about those constraints. And then we're going to assume those constraints when we go about actually finding the points in the next lesson. So in general, in the case of two calibrated cameras, we had talked about parallel optical axes, all right, so that they were lined up and the planes were coplanar. But of course, they can be what's called verged. They could be pointed in some particular way. In fact, they don't even have to necessarily be verged on the same point. Usually they are, because we're used to human systems. But what we're going to do is we're going to talk about epipolar geometry, the epipolar constraint, in both of these cases. So let's start it this way. So if I have an image on the left and some point P projecting in that image, the question is, where can P prime, the image of that same point on the right, be? Well, basically, the actual scene point could be anywhere along the ray that contains P prime. Each of these red dots correspond to possible locations along that ray of the actual scene point that's projecting to P prime. Now remember, in perspective projection, one of the things we said was that lines project into lines. So the line containing the center of projection and the ray that goes through that point, that's a real line in space. Okay? That line must project into a line in the right image. So that's the constraint we're going to talk more about. So looking at this geometry a little more carefully, the geometry of two views constrains where the corresponding pixel will be. So the point P that projects into the image, well, it could be out here in the world, that red point P. Or it could be at P1, or it could be at P2, or it could be anywhere along that ray in the left image which projects to that line in the right image. That line is called the epipolar line. This line is carved out by the plane that contains both image centers and the actual point, or just this ray. That plane intersecting the image plane, and the intersection of two planes is a line, that's the epipolar line. Now, of course, the reverse is also true, right? So that same plane corresponds to this epipolar line. Okay? These corresponding set of lines, these corresponding set of epipolar lines, provide the constraint that we're looking for. Any point in this image that's on this line, its match must be somewhere on that line and vice versa. And this is called the epipolar constraint. In epipolar geometry, there are a variety of terms that we use all the time, and you should become familiar with them. First is the baseline, which is just the line or the ray in space that joins the two camera centers. The epipolar plane for a given point, I probably should say for a given point, contains the baseline and that point. So this point, this camera center, that defines a plane, and that's our epipolar plane for that point. As we showed before, the epipolar line is an intersection of the epipolar plane of a given point with the image plane. It really should say the image planes because there's always a pair of epipolar lines. Corresponding epipolar lines are, if you have a point on one epipolar line, then, or if you have a point, you figure out its epipolar line, and its matching point must be on the corresponding epipolar line in the other image. Finally, we have something that we haven't talked about before, which is called the epipole. The epipole is the intersection of the baseline ray with the image plane. So assuming the image plane is big enough, right, the image plane is small, it might not, but if the image plane were big enough, it would intersect the image plane there. So you should be clear, right, that since all of the epipolar planes intersect the epipoles, because it contains this ray, that means that every epipolar line will also intersect the epipoles. We're actually going to see that in just a minute. So why is the epipolar constraint useful? Well, we've already said that basically the epipolar constraint reduces the correspondence problem to a one-dimensional search along the epipolar line. In this particular case, we have parallel epipolar lines. We'll see that in just a minute. But the red dot on the left that's located in the window of this beautiful chapel, wherever that is located somewhere in this epipolar line on the right. So I search for the middle of the window. I don't have to look all over the image. I'm just looking along the corresponding epipolar line. So what do epipolar lines look like? And we'll consider two cases. There's the general case on the top where we've got verged cameras, and then there's the special case where we have parallel optical axes. In the verged case, drawn here, you can take a look at the epipolar lines by considering a couple of different points. So remember, each point defines a pair of epipolar lines, and here they're drawn. And so here's an example of epipolar lines of two verged cameras. And what that means is that, for example, this point here, since it's on this, happens to be on this line, must be somewhere on that line, and in fact, there it is. Okay? And this point here. Now, only a few lines are drawn on here. Of course, if I was looking for this point here, there is some epipolar line, because there's some point here that defines an epipolar plane, and there would be a corresponding epipolar line on the other side. We've only drawn in a few of them. So here's a question for you. We said that all the epipolar lines converge at the epipole. Well, where's the epipole? Well, let's take a look at just this image on the right. The problem is that this image ended here. If this image were huge, this line and then this line, here's where they would intersect. Okay? So the problem is that the image, if you will, is sort of cropped. The image sensor is too small to actually find the epipole. The epipole is a mathematical construct that's the intersection of the baseline with the infinite plane that contains the image plane. So that's why the epipolar lines look like they would converge, but they do it off the screen. Now, let's consider the case where we have parallel image planes. It's a little hard to see here in the picture, but the idea is I've got two image planes. My centers of projection are sort of out here, and any point defines a plane that intersects these image planes, and it's what's called actually a pencil of planes. These planes rotate around that baseline, but we have parallel image planes. What do the epipolar lines look like? Well, they look like this. In this particular case, because of how they're shifted, they're these horizontal lines, and you can see that for the corresponding 3 points located on that chapel, they land, 4 points, sorry, that they land somewhere on these epipolar lines. So if the epipolar lines are all supposed to intersect at the epipoles, and here we've got these horizontal epipolar lines, where are the epipoles? Well, as somebody once explained to you, somewhere in some metaphysical space, sometimes various hallucinogens were involved, parallel lines intersect at infinity. Okay, so essentially the epipoles are out at infinity. If you're not sure about that, travel to the Himalayas and ask somebody high up on a mountain, or just high up anywhere. I don't know if I'm allowed to say that. Just ask them about parallel lines. And the idea is that parallel lines here essentially are infinity. One way of thinking about that is as the two planes get closer and closer to being parallel, the epipoles keep moving further and further. And so when you take a limit, when they actually become parallel, then the location of the epipole is at infinity. That brings us to a quiz. Let's consider these two stereo pairs. We have the top one, which you know the cameras are verged because those lines intersect. But the bottom one, I'm going to tell you, is from an image pair, stereo pair, that has coplanar image planes. And the question is, how do you know that image B has a parallel image planes? And I'll give you three choices. A, the epipolar lines are horizontal. B, the epipolar lines are parallel. And C, because I just said B had a parallel image planes. Well, you might think, and I'll go back to here, that it's because they're horizontal that we know that they're parallel image planes. But actually, parallel image planes mean that the epipolar lines are all going to be parallel. The only reason they're horizontal is because I happen to be holding the camera in such a way, the pair of cameras, that the baseline between them is horizontal with respect to the vertical in the image. Right? So basically, if I had held things this way or rotated my one camera that way, I would still have parallel epipolar lines, because the epipolar lines are defined by the geometry of the camera center and the point. That is the plane. They just have to be on a plane, but I can shift them up and down. I can rotate them, and that will rotate my parallel lines. So it's not the horizontal epipolar lines that tell you that they're coplanar, but the fact that they're parallel. That ends the lesson on epipolar geometry. In the next lesson, what we're going to assume is that we know the epipolar lines. In fact, most of what we'll talk about will use horizontal, parallel, lined up epipolar lines. And then we'll go about solving the correspondence problem. Welcome back to Computer Vision. Today we're going to talk about stereo correspondence. Up until now, we've defined the epipolar geometry that talks about how the two views relate, and how if you have a point in the left image, then if you know the camera's relation, it's a one-dimensional search. And in general, the epipolar lines can be, well, arbitrary, not arbitrary, but skewed in a variety of ways and located. But today, in order to make life easier, we're going to assume a bunch of simplifying assumptions. For example, we're going to assume basically the geometry that we drew out last time of parallel or coplanar, actually, image planes. We're going to assume the same focal lengths of the two cameras. We're going to assume that the cameras are horizontally aligned at the same height, and that the images are pulled out such that the epipolar lines are horizontal and that they are in fact lined up. So a XY location in one image is at a different X, but the same Y location in the other image. So look, that's a lot of assuming, and for real stereo, you wouldn't be able to do that. You'd have to do a rectification of the image first. We'll talk about that a couple of lectures from now. But for now, we'll make these assumptions which will allow us to attack the correspondence problem more easily. And in fact, it's the way you're going to be doing correspondence on the problem sets. So what is the correspondence problem? Well, basically, the epipolar constraint constrains what our solution is, but it doesn't solve our solution. So here we have a bunch of points in the left image, and we know they lie along the epipolar line in the right image, but the question is, what are the matches? And here in hypothesis 1, 2, and 3, coded in gray here, you can see these are different possible matches. And so for each point in the left image, we have to decide what the match is in the right image, or vice versa. So to help solve the correspondence problem, what we need are some additional constraints. The epipolar constraint was a hard constraint. That is, it must be true. It's enforced by the relative camera geometry. But there are other types of constraints which we might call soft constraints. One is similarity, which says that pixels in the left image should look about like the pixels in the right image if you have the right match. Uniqueness says that there's up to no more than one match of a left pixel in the right image. Ordering says if pixels go ABC in the left image, they go ABC in the right. And disparity gradient is limited. That means that the depth depth doesn't change too quickly. We'll talk about some of these today, but what we're going to start with is similarity. Similarity is essentially saying that the image patch from the left should match the image patch from the right. So to find matches in the image pair, we're going to assume, first of all, that most points that are visible in one view are also going to be visible in the other, so we'll go looking for them, and that the image regions for the matches are similar in appearance. So here's how we're going to do the dense correspondence. And dense correspondence meaning we're finding a match everywhere. For every pixel, let's say in the left image, and we're going to take a little window around that pixel, we're going to compare it with every pixel/window in the right image. And we're going to just pick the position that is either the most similar or the least dissimilar. And that best match, that's what we're going to assume is our corresponding point. So here's a very simple illustration. So I have a scan line across both images, and we're assuming parallel scan lines for now. And I've got my window in my left image, and I'm going to compare it to a bunch of windows in my right image. And the matching cost is computed everywhere, and so this is just a notional description of what the matching cost is, a function of disparity, so how far off I am from the first match. And of course the idea is, well, we're going to pick the value that has the best score. So I might use something called sum of square differences, which is the sum of the square differences. Wasn't that a surprise? No. What you do is you take the two pixel windows, you overlap them, you subtract them, you square the differences, and then you sum them up. So that would be a measure, and that's why at the top it says dissimilarities. Now, sometimes, let's suppose one image was a little bit brighter than the other image. You know, for some reason the gains weren't set so well on the camera. If I just do direct subtraction, even if the match is exactly the right place, because of that scaling of the intensity, I'm going to get square difference error, and it might not lead me to get to the best match. Now, we've already talked about how to eliminate the problem of scaling. Remember, we talked about doing normalized correlation, where we scale the value of the window so it has the same standard deviation. So you could do that here too. You could take your window and slide it across doing normalized correlation instead of sum of square differences, and that's actually a similarity constraint.
All right, let's try to do this in code. I want you to write a function, findBestMatch, that takes two arguments, an image patch and a strip, which is basically the same height as the patch but has a width equal to that of the image. Your function should return the x-coordinate where the patch is found in the strip. Here is some test code. Let's load up two images from a stereo pair, left and right. This is the left image, and here's the right one. If I switch between the two, you can see some key elements moving. Alright, let's convert these to grayscale, double type, and scale them down to 0-1 range. Here are the grayscale versions, left and right. Okay, let's define the location and size for the patch we want to match. Let us extract this from the left image. Here's what the patch looks like. Using the patch specifications, let's extract a strip from the right image. Note that here, since we want to go across the width of the image, we select all the columns. And here's the strip from the right image. Once you have implemented your function, call it by passing in patch left and strip right. You should be able to use the best x-coordinate found to extract a patch from the right image. Go ahead and give it a shot. Let's use sum of squared differences to find the best match. Let's initialize a couple of variables we'll need, and then let's run through the strip, placing the patch at every valid location. We extract a second patch of the same size from the strip at each location, and then compute the sum of squared differences, and keep track of the x-coordinate that gave us the minimum difference. And that's about it. Let's see how it works. Okay, so the best x-coordinate found was 145. The top patch is from the left image. Here's the strip from the right image you saw earlier. And the bottom patch has been extracted from the right image. Notice that the appearance of the top of the house has changed a little bit, but our algorithm is still able to find it correctly. Now, instead of using sum of squared differences, you could have also used cross-correlation. Feel free to try out alternate methods.
All right, so let's continue looking at this correspondence problem a little bit more. Here we have two images. This is courtesy of Andrew Zisserman. And we've got an epipolar line, and again, we've got horizontal epipolar lines. So here we have both scan lines, left and right image, and a plot of the intensity profiles. And of course, they're going to look pretty similar because there should be matches along the way. But, you know, there are slight differences in exactly what the profiles look like. There's a little bit of noise. And there also might be some ambiguity, so finding where you match over here might be challenging over there. So we're going to look at this a little bit more carefully. We've pulled out a window on the left, and we're going to slide that along the epipolar line, that window on the right. All right, let's take a look at a particular window. So I'm showing you the two little bands that are sort of the height of the window. And from the left image band, we're going to pull out a particular point. All right, so here's this point and this window that's associated with it. So that means we have to pull out the right band. That's the same, it's the epipolar band, if you will. It's the epipolar line, but with the window height. And we're going to slide that window from the left across the right band. And if we do that, and we were doing, say, cross correlation, well, you would see this nice high peak right where the thing is supposed to match. So the window was picked sort of between these two dark squares here, and of course the best match is right between these two dark squares, just like you would expect. The problem, of course, is we put a window over a nice, essentially, in fact, it looks a lot like a surveyor's target of black squares and white squares. What happens if our window falls over this area on the left image band that's pretty textureless? I mean, there's some variation in intensity. It's a little hard to see here. Now, if I correlate that with the right band, what do I get? Well, I see a result that looks like this, okay? And, of course, the question is, where's the match? Because you notice before I had a nice strong match above that 0.5 value. Now I get multiple matches, and I know that the match is supposed to be somewhere where the question marks are, but it'd be pretty hard to justify picking that one over any others. So how could we fix this? Well, our problem, of course, is that the window was so small that it didn't catch any sort of significant texture.
So which regions in this image do you think are good for stereo matching? Mark the checkbox next to each suitable window. Let's assume that our stereo setup has coplanar image planes and that the epipolar lines are horizontal. You've seen two of these already. The one with two black corners jutting in turned out to have a very strong match. And we saw that this area on the wall was essentially featureless. Similarly, any region that is too bright or too dark has too little information to be useful. Also, regions that only have horizontal edges going through them, like this or this one, are not useful in our stereo setup. This is because they could result in multiple matches along the epipolar line. Okay then, which ones are good? Anything with a fairly distinct corner works. So do regions with distinct vertical boundaries. If you consider the epipolar lines going through them, you'll see that there is no other region in the image along that line which matches the region.
You could say, well, instead of using small windows, use a slightly bigger window. So there's this question of how should we pick the window size? And just like when we were talking about scale, there's not going to be any easy answer. Here's an example of another stereo pair. I'm only showing you the left. So if I do a sliding window stereo, well, for a small window size, well, gee, I get the branches pretty well of the tree, but you'll notice there is all this, I think the technical word is crap, all over everywhere else. That is, this is a disparity image, and my ground should be going from near to far, and there shouldn't be all this junk all over it. So what do? Well, obviously, because of noise and things, I need to make my window bigger to get a more robust match. So if I make my window bigger, I get this nice ground pattern here, right? You can see that it goes from near to far. Okay, and the trees back here are farther away. But notice what happens to the tree branches there. Okay, the window is too big, and when you put it over a branch, it gets both the branch and the background and doesn't know what to do. Just as I said earlier in this course, scale is always an issue. There's no magic answer. I want to talk just a little bit about two of these other constraints that we talked about for the correspondence problem. I'm not going to talk a lot about them, just give you some insight. One is uniqueness and the other is ordering. So uniqueness says that there's no more than one match in the right image for every point in the left, and vice versa, same thing. Okay? So why does it say no more than one? Shouldn't it be exactly one? Well, no. The problem is occlusion, and that's illustrated here. Let's suppose I have a green bar in front of a red bar. All right? So here's my left image, and here's my right image. And these are the pixels being seen in my left image, and these are the pixels being seen in my right image. All right? You'll notice I have two red ones here, then two green, then a red. And here I have a red, two green, and two red. And the problem is that these pixels are occluded. And what we mean by occluded is that they're only visible, sometimes they're called half occluded, because this pixel is only visible in the left image, and this pixel is only visible in the right image, right there. Okay? This happens at occlusion edges. So if I hold it like this, so if I ask Megan to close her left eye, your other left, she can't see this thing with her left eye, but if I ask her to change her other one, she can see it with the right eye. So the tip of this finger is only visible in one of her eyes. So that's why you don't have necessarily a unique solution that every pixel is matched in every frame. The ordering constraint basically says that if I've got pixels in my left image that go A, B, C, they're going to appear in the same order A, B, C in my right image. And that's typically what happens when I look at a single solid surface. So when is this violated? Well, duh. When I'm not looking at a single solid surface. That's SSS. That's pretty cool. So what's not a single solid surface? Well, a couple things. First of all, we could be not solid. Now, what does it mean to be not solid? Well, suppose you have a surface that's transparent that has some markings on it. Okay? So here we have this, suppose this is a transparent surface, all right, and we can see these points, all right? Well, if they're transparent, it would go A, B, C in that order, but over here it would go C, A, B. All right, and that's just because we can see through the surface. Well, that's really weird, and that almost never happens. What happens much more often is what's sometimes called the floating pen, I forget, whatever it's called. Basically, if I've got a narrow occluding surface, and you can actually do the simple experiment, having nothing to do with stereo, of put your two fingers, one right in front of the other, and in your left eye, this finger is to the left of this, but in your right eye, the other finger is to the left of this. So it swaps. So if you're a stereo algorithm that's trying to figure out how to do the match, that's a problem. I will tell you that current stereo algorithms do a lot of work to handle the occlusion problem, because that happens all the time, because if I've got one edge of an object in front of another object, there are going to be pixels that are visible in one eye or one camera and not the other. Current stereo algorithms are not so great on violations of the ordering constraint, because of various scale problems, etc. So that's just sort of where the state of the art is.
Let's try to implement a very simple approach for matching corresponding regions from two image strips. First, recall the find best match problem. Given an image patch and a strip, your task was to find the best X location for the patch in the strip. You are free to use this reference implementation or roll your own. Now, your task is to match two strips. You're given the two strips, left and right, as well as a block size B. Note that you're only to consider whole, non-overlapping blocks. This means if your strip is 640 wide and the block size is 100, then you only have 6 whole blocks. The last 40 columns of the strips are unused. Return a vector of disparity values, one for each block. Alright, here's some code to test with. We use the same pair of flower images as before and extract a strip from each image. The top one here is from the left image and the bottom one from the right. Now we should be able to call your function by passing in the two strips and the block size. So, how do you go about solving this? Let's first figure out what the number of blocks should be. Since we are only interested in whole blocks, we use the floor function to round off. Okay, now initialize disparity as a row vector. For each block, let's compute the x-coordinate of the left edge. Note that MATLAB and Octave begin indexing at 1. Use this to extract an image patch from the left strip. Now find its best matching X position in the right strip And finally, compute disparity as the difference between x positions in the left and right images. Okay, let's run this. 6 disparity values as expected, but they don't make much sense, do they? Let's try to plot them. Okay, so what does this 0 in the first block position mean? Well, it just says that the best match for the block in the left image was found at the same position in the right image. How about the peak at position 2? This says that the second block has apparently moved a lot. You can actually verify this visually. Look at this feature in the left strip and its position in the right strip. Different blocks have apparently moved by different amounts. Now, how do these disparity values relate to depth in the scene? Think of what are the drawbacks of a simple approach like this.
We've taken a look at correspondence done in a simple fashion. And in fact, that simple fashion is what you guys are going to do on your problem set. I want to take a look at a couple of slightly more sophisticated methods that are actually closer to the state of the art in stereo. There are a couple of ways we do that. There's a bunch of stereo pairs out there for which there is known ground truth of depth. So here's one from the University of Tsukuba. It's a well-known scene, and the image on the right is the actual depth. And these things can be generated a variety of ways. You use a laser scanner, some other method of being very precise in doing the matching. But the idea is, if you're developing a stereo algorithm or you're doing a paper or something, you have a scene for which you can say, I know what the actual value should be. So the types of methods I was showing you before, which are window-based matching. On the left here, we have sort of the best result of a window-based match, and on the right is the ground truth. And we're using a false color image here. It makes it a lot easier to see mistakes. If everything was just gray values and disparities, it's harder to see how things have changed. And you'll notice that it does an okay job. You know, the mannequin head is in front of other things, but it really does a pretty crummy job around the edges. This movie camera in the back, whoops, bad color. This camera in the back is sort of all eaten up here, never mind what's going on over here. So it has some general difficulties. And what we'd like to do is to see if we can get a lot closer to that ground truth solution. So better solutions do something more than just individual correspondence estimates. All right? Essentially, what they want to do is they want to optimize the set of disparity assignments in some sense jointly. Meaning that I don't just assign this pixel to somewhere and then this pixel independently. I want to think of all of the assignments together in some way and come up with an optimal solution. And this can be done at least two different ways. One is to do a scan line at a time. So we're still going to do a line at a time, but for all of the pixels in that line, we're going to think about how we want to do the assignment, and then we do that for each scan line. And then even more modern methods, and ones that get even more improvement, they actually do it on a full 2D grid. So we're not thinking just across the scan line, but vertically as well. So let's talk about the scanline methods. So here I have that Tsukuba University picture again, and we have two intensity profiles, the left and the right. All right? So just to be very precise about it, we have a 1D signal here and a 1D signal here, and we have to match every pixel here to some pixel somewhere over here. All right? But what we want to find is we want to find the best overall match. That is, the whole set of matches, we want the best set. So the way this is done is in what's called a dynamic programming formulation. And it's a little complicated, but bear with me. So what we have here is, I'm going to pretend that I've got the left scan line signal down here, and each of these is supposed to be the pixels, although I notice there are more dots than pixels, so assume that there's as many squares as there are dots in this grid, and same thing over here. And let's assume for a moment that we know that the leftmost pixel here corresponds to this one, and the rightmost pixel there corresponds to that one. All right? Well, then a solution to the mapping of the left to the right is just the path from that top left-hand corner to the right bottom right corner. So there's a particular path, okay? And the goal is to find the best possible path. And best possible path meaning the least cost. Now, when you're located somewhere in this grid, there's only 3 different ways that this path can go. The simplest way is when you go on the diagonal. Now, when you go on the diagonal, What it means is if this pixel was mapping to this one, then this one is mapping to the next one. That is, they're staying at the same disparity. So if I have to go +3 to match this pixel, then this one's also +3, and I just keep going along. But suppose I have some pixels that are visible in one image and not visible in the next. So here I have an area that I'm saying is left occlusion. What I mean by that is visible to the left eye and is not visible to the right eye. So what that means is that all of these pixels, this range here, are all being mapped to this one location. So you can think of it as that this pixel was mapped to this pixel, but all of these were not seen. So that's a left occlusion. Correspondingly, you can have right occlusions. All right? And the goal is to find the least cost through. Now, when you're going diagonally, your cost is just the match between two pixels. And that can be a match much like we did before. Did normalized correlation or sum of square differences, depending upon whether you're doing similarity or dissimilarity. But when you're not going the one-to-one, but you're actually doing the occlusion, what you need to do is pay a price for occlusion pixels. And a variety of methods have been designed that tell you, that say how to try to assign that cost. Some of them are Bayesian, some other ways. Now, for those of you that know about shortest path or Dijkstra algorithms or other forms of solving this, this can be formulated as a dynamic programming problem. And dynamic programming approaches are nice because they're computationally efficient. You don't actually compute all possible paths, and yet you can still compute the best possible path. And the only thing requires is that you basically have to be able to evaluate the costs of going horizontal, vertical, or diagonal. And here I've listed some references, including one by this Bozo-Bobic, that showed about how to do that. We introduced this thing called ground control points, which was a cool way of not being very sensitive to the occlusion cost value that you use, which was part of the problem of earlier methods. But this is in the waybacks. Looking at that Tsukuba University thing again, here you can see that with the dynamic programming, we get a lot better solution than we had before. Things are doing better here and quite a bit better there. But one of the things you'll notice is that you get these streaks, and that makes sense because every scan line is done independently of the other scan line. So it doesn't know anything about the previous solution, so it makes sense that as you change scan lines, you might actually get a reasonable shift. And unfortunately, you can't use dynamic programming to find a spatially coherent set of disparities over a two-dimensional grid. You have to do another approach. So in motivating that other approach, let's think about it this way. What defines a good set of correspondences? Well, first of all, going back to our earlier work, we want each pixel to find a good appearance match from left image to right or right to left. So we talk about match quality. But the other thing is, remember when we were first doing filtering for noise, we said one of the assumptions we make is that two pixels that are nearby have similar sort of real values. Well, when you talk about depth, you can also talk about how two pixels that are nearby have a tendency to have approximately the same depth. So that means that they probably should have about the same disparity. So if this pixel has to be shifted over 4, the one nearby shouldn't shift a whole lot. Okay? And I might want to penalize solutions that have lots of jumps. So the method that we're going to use now looks at both of those things. And it thinks of solving stereo as an energy minimization problem. The first term, the energy I should define that here we have I1 is the left image, I2 is the right image. We've got a window on the left. We're going to look at it across the right. But then all the way on the right is a disparity image. Okay, so that's the disparity that we compute. And our energy as minimization approach requires two energy terms. The first term is a data term. And the data term just says that summed over all the pixels, that the window subtracted from the window on the other image, so this window minus that one, squared, should be as low as possible. So we want, if we're going to do an energy minimization, our data term basically takes a look at the squared of the differences. That's similar to what we were doing before. So one way of thinking about it is when we were doing correspondence through dense search, we were only looking at the data term. The second term is called the smoothness term. And you'll notice that I don't have any window here, I don't have any window here. I'm only looking at the window over here. And in fact, in the smoothness term, you'll see that the image doesn't come in here at all, neither the left or the right. I'm only looking at the windows of the neighbors in the disparity image. This is the disparity image here. All right. Now this row function, this is a function that's essentially a robust norm. So what you want is, it's okay to make small amounts of change, and then it should get expensive to make large changes, but it shouldn't get even more expensive to make even bigger changes, because that's going to be sort of a jump at an occlusion. So that row function is meant just to be a robust, I mean, you can think of it as a square that maxes out. But that's our smoothness term. And for energy minimization, what we do is we have the total energy, which is a blend of the data term and the smoothness term weighted by these coefficients. And what you want to find, and this is the hard part, is you want to find an assignment of disparities that minimizes this energy function. So the bad news is that it's hard to do. The good news, no, that's not right. It's not hard to do. You're master students in computer science. Hopefully some of you have seen the graph cuts algorithm. I'm not sure. We may do that later in this class when we do an algorithm thing for segmentation. Graph cuts is a well-known computer science algorithm where you've got two groups of graph. You have a graph and you want to cut it in such a way that minimizes some value. The cool thing was that Boykov, Wechsler, and Ramanzabe applied graph cuts to some computer vision problems, and in particular, they applied it to this stereo disparity problem. And when you do that, you get a result that looks like this. And this is pretty good. So on the right here, we have the ground truth. All right, and on the left, you have a picture that looks pretty close to that ground truth. There's still a little bit of issues. I guess green's a bad choice here. Pick red. There's still some issues around here, and of course a little bit with where the occlusion happens. Because remember, we've got occluded pixels near the edges. But in general, compared to that correspondence solution that I was showing you before, it's a much better solution. I also point you to this Middlebury stereo website. There's a whole bunch of ground truth and sort of standards in stereo that's available there. I don't want to give you the impression that stereo is a totally solved problem. There are still some challenges. Textureless areas, it's very hard to know exactly where the match is, and clearly the surface has to have more influence. Occlusions are still a challenge. Violations of the brightness constancy, so things like specularities whose position on the surface move as I move, that violates our stereo. Really large baselines, so I've got a camera way over there and a camera way over there. Well, now I've foreshortened things, right? So here I see the front of the camera, and over here, probably I'm out of the field. Probably Meg can't, I'm totally gone. Well, but all I see over there is the side of the camera. So if I want to do stereo matching, that's a very hard thing to do. And then there's camera calibration errors, right? So remember the camera calibration defines for me the epipolar lines. What if they're wrong by a little? Well, then my epipolar lines are wrong by a little. So how do I deal with that? So these are challenges for ongoing stereo research. So that ends the lesson on stereo matching. In fact, that ends all of our lessons on stereo. You're going to implement the simple correspondence method. By the way, for a more advanced version of this class, we asked to do the energy minimization by either implementing or using a library for graph cuts. If you're so disposed, you might find that a really cool thing to do. When you go to implement this simple version, hopefully you're going to be impressed by two things. One is, it doesn't work nearly as well as I implied it would work, and I even didn't even imply it would work well at all, so that's really going to be. However, your computer will be seeing in 3D. You're going to give it two pictures, we provide you the pictures, and your computer will recover the depth. You know, up until not that long ago, that was considered magic done by human beings' brains that was not understood. And now you can do it on your iPhone if you had two cameras. Anyway, I hope you'll find it cool that you can recover that depth. That ends for stereo. Talk to you soon. Welcome back to computer vision. I hope it's welcome back, because if you're jumping in now, you missed some really good jokes in some of the better lectures. This one's okay, actually. All right. Anyway, today we're going to talk about extrinsic camera calibration. We'll define what that means in a minute. We took a little hiatus to talk about stereo, so you guys could get working on your stereo. And stereo was our first look at multi-view geometry and multi-view cameras. And we talked about how, in order to do real depth reconstruction, we have to understand the geometry of what's going on between the cameras. And that's what we're going to start talking about today. So before the stereo thing, the stereo sections, we introduced projection, perspective projection. And here was the model that we used. In particular, we had a system where we had a center of projection that was located at the origin of a three-dimensional camera system. And then we derived from similar triangles the location on the image of the point projected down onto the image plane. And then in order to figure out where the point was going to land on the image, we just eliminated that last coordinate. Now we said that this was a bit of an issue because this division by z was nonlinear. And because we had to pull out the particular z, it wasn't a constant z, it was the particular z. So we introduced this notion of homogeneous coordinates. And the homogeneous coordinates essentially added another component to the vector, and if it was 2D, it became a 3-long vector, 3D became 4. And the idea was that we were going to be able to convert from homogeneous to non-homogeneous when we needed it. But before we did that, all of our operations could be done through matrix multiplication, which, by the way, made homogeneous coordinates, the whole thing invariant under scale. I could scale a coordinate, homogeneous coordinate by anything, and when I did the normalization, divide by w here, it would go away. And one of the reasons we did this is we said that perspective projection could now be done as a matrix multiplication. So here I've written 1, 1, and here we've got 1 over f. And by the way, just to make life easier, I'm using the absolute value of z, so we don't have to worry about z being positive or negative. So when I do the multiplication, I get this homogeneous coordinate, and when I want to normalize and go to unhomogeneous, I get the uv by dividing it out. But in all of this discussion about projection, we have the notion of a camera's coordinate system. By the way, I'm going to go like this, and it's not some like weird curse in Georgia. It's a coordinate system, 1, 2, 3. Okay, so we have an origin and a coordinate system. And we said that we put the center of projection at the camera's coordinate system, and with the z-axis, the optic axis going down the z-axis. So to do geometric reasoning about the world, we need to be able to relate the coordinate system of I guess I'm going to have to do this. We have to relate the coordinate system of the world to the coordinate system of the camera. And in fact, today, what we'll do is the coordinate system from the world to the camera, and then today, I don't know when you're going to watch it, next month, the next lesson will be the coordinate system from the camera 3D coordinate system to the image. This whole thing falls under the labeling of geometric camera calibration. In order to be able for the camera to tell us about things in the world, we need to know the geometric relationship between the camera and the world. For reference, you can take a look at the Forsyth and Ponce book. The sections are listed here, and there's a nice description. So as we said, geometric camera calibration is composed of 2 parts. There's the first part that goes from some arbitrary world coordinate system, put your origin wherever you want it to be, to wherever the camera is, and that basically tells you where the camera is in the world and its pose. And then the second one is from the 3D camera to the image plane. The first one is called the extrinsic parameters. That's the extrinsic. It goes from the world coordinate system to the camera coordinate system. The intrinsic, which we'll do next time, is from the 3D camera system to the image. So let's talk about camera pose, or the orientation and location of the camera frame with respect to the world. In this diagram, this transform T is a transform that goes between the world and the camera system. Okay, and that's what this T with lower W, upper C is going to mean. All right, we're going to talk more about this notation in a minute. The transformation that we're going to talk about is this going from world coordinates to camera coordinates. So that's a good time for a quiz. How many degrees of freedom are there in specifying the extrinsic parameters, in specifying the relationship between the world coordinate system and the camera coordinate system? A, 5, B, 6, C, 3, it's three-dimensional space, or D, 9. Okay, well, let's take a look. This slide says for rigid body transformations, we need a way to specify the 6 degrees of freedom of a rigid body. So the answer was 6. But why 6? Well, you can easily think about it this way. Let's define a rigid body as just a collection of points whose relative positions to each other can't change. And for the mathematicians in the audience, we're going to pretend that's a well-defined statement, okay? Or you can think of it as a box. So the first thing I can do is I can locate that box in 3D. I can take one point of that box, say the corner here, and figure out the x, y, and z location of that box. So that's 3 degrees of freedom. Then I can take some other point on that box, let's say the corner, and I can move it around. Now, I can't change its location in space arbitrarily because I'm holding this point fixed. So essentially, this corner can move around on the sphere. So this point here can be moved around anywhere on the sphere. So this is supposed to be like rotated backwards this way. All right? And just the way you can think of on a globe from the middle, there's a latitude and longitude to get any location. There's 2 degrees of freedom of a vector's direction. So that's another 2 degrees of freedom. So we're up to 5. And finally, once I have this vector specified, I can rotate, I can spin about that vector. So the cube here, as indicated by this fancy Microsoft PowerPoint arrow that's in here, we can rotate it about that diagonal. So that's 1 more degree of freedom. So that's why there are 6 degrees of freedom for a rigid body. I'm going to assume most of you knew that already, but there you go. That's why there's a fast forward button. So now life gets ugly. I'm going to be using the notation from Forsyth and Ponce. It might not be the best notation, but it is a notation for dealing with coordinate transformations, which is what we're going to be doing. So the idea here is that superscripts are going to represent what coordinate frame you're in. So here I have some point P, and I've got the A coordinate frame. And the expression of the location of point P in the A coordinate frame can be thought of as a variety of ways. You can think of it as the location x, y, z in the A frame. But if you remember a little bit from your, I don't know, algebra, calculus, the right way of thinking about the vector that goes from the origin to P, that's this vector here, is it's got the I component of the amount x, the j component of the amount ya, and the k component of the amount za. So a vector is actually the sum of these 3 components, the I component, j component, k component, each scaled by the coefficients x in A, y in A, z in A. Suppose I want to express the location of point P, whose value I might know in coordinate frame A, but I'd like to know where it is in terms of coordinate frame B. Well, that's just a translation. And it's handled very simply by saying the location of P in B is just the location of P in A plus the location of the origin A expressed in the B frame. All right? And so that equation just gives us that new offset. And this OA in B, that's just a 3 vector. That's the offset of the origin of A in the B frame. I told you this was ugly, but we have to slog through it. The good news is, once again, homogeneous transformations, or I should say homogeneous coordinates, are going to come to our rescue, where translation can be expressed as a multiplication. So we've rewritten this top equation, P in B is equal to P in A plus OA in B, as this matrix transformation. A couple of things. First of all, that's a 3 by 3 identity matrix. So this is, and since OA in B is a 3 by 1. This is a 4 by 4 matrix, which means that this vector down here, that's actually a 0 vector of length 3 transpose, so it's 3 zeros in a row. It's actually 0, 0, 0, and this is 1, 1, 1, 0, 0, 0, 0, 0. That's clear, isn't it? That's why we draw it this way, okay? And just to remind you, translation is commutative, okay? And you can actually show that in the matrix multiplication if you wanted. Now life gets uglier. Rotation. What I have here is a figure, or I think this is also from Forsyth and Ponce slides. And what I'm showing you is 2 coordinate frames, A and B. And you'll notice that A has an I vector, a j vector, and a k vector, and B has an I vector, a j vector, and a k vector. And one of the important things to realize is that this P value, the vector from the origin, can be expressed in 2 ways. It could be expressed as some components in the A frame times the x, y, z components, or some components in the B frame with the components in the x, y, and z frame, right? They're the same vector, right? And what's key is understanding that there are these basis vectors, and we need to know the amount of component that multiplies each of them. What we want to be able to do is say we're going to rotate the frame from A to B. And that's what this says. What this says is, given my point described in A, I'm going to have a rotation operator that will give me the P now expressed in the B frame. And R A to B means describing frame A in the coordinate system of B. And it says, so if you gave me the location of a point in terms of the components of A, this is, and it's only a rotation, after applying R, I get the components in the frame B. So what does R look like? Well, there are two ways to think about this. First, we'll think about it the hard way. R A to B expresses how each basis vector in A would be expressed in terms of B. So the first column of RAB is the component of the I vector of A expressed in terms of how much it has in the I direction in B, in the J direction in B, and in the K direction in B. So you can think of it as like the dot product between IA and each of the components of B, IB, JB, KB. And likewise, each of the following columns is that way. So one way of thinking about this is that the columns of RAB are the I vector of A expressed in the B coordinate frame, then the J vector of A in the B coordinate frame, and the K vector of A in the B coordinate frame. All right, so why is this true? Well, let's think about it this way. Suppose I had a point vector in the A frame, Harlem, that was just at value of 1, 0, 0. Okay? So what that means, it's actually a distance of 1 in the I direction of the A frame and none in the J and K of the A frame. What should the value of that be? All right? And I'll just write that down here. Well, this multiplies this to that. So it would just give me the IA dotted with IB. So the first component of the transform frame is just the I vector's amount in the I direction of B. Well, now let's go through this. We go 1, 2, 3. It's going to get IA dot JB. Okay, and again IA dot KB. In other words, I mean, it's just what it says here is that what we have to get out if we had just a 1, 0, 0 needs to be how that vector is dotted with each of the components. And that's why this matrix can be thought of as having its column vectors as just being each of the basis vectors of the A frame expressed in terms of the B frame. Do you get that? So on the slides you'll have that, so just press the pause button and that way you can see what's going on. Just to remind you, I labeled this that the columns of the rotation matrix are the axis of frame A expressed in frame B. Why? Because we just went through all that nonsense showing it to you. By the way, it can also be thought of as the rows are just the column, are just the basis of the B vector expressed in the A frame, right? So here's IB in terms of the I component of A, here's IB in terms of the J, here's IB in K. So if you think about this, is that if I were to transpose that vector, so I made the columns the rows the columns, I would now have, instead of RAB, I'd have RBA, all right? This is an orthogonal matrix, right? The orthogonal matrix, all of the rows, all of the columns are unit vectors that are perpendicular to each other. So the determinant, so the magnitude determinant is 1, and it's your traditional rotation matrix. And by the way, really important is that the inverse is equal to the transpose. So if you had a rotation matrix and you want to go back and forth between the two, the inverse of the transpose, which realize it has to be because the inverse of RAB has to be RBA. And we just showed how the rows are the sort of the transpose with respect to the columns. So let's take a very simple example. So here I have two frames, and I'm telling you that the rotation of A to B is just about the z-axis. So the image on the right, I'm looking down on the z-axis. Now this should look very familiar to you when I ask you what is the rotation matrix. Why? Because you did this in algebra, right? You talked about just rotation of an angle theta about the origin when you were doing xy. And hopefully you remember something that looked like this. See, it says cosine theta, minus sine theta, sine theta, cosine theta, right? George Thomas, who wrote the calculus textbook that many of us use, taught it to me as Charlie's little sister socked Charlie. That way you remember where the minus sign goes. Anyway, so The point is that this matrix here is just for rotating the x and y, keeping the z constant. So if I wanted to get an arbitrary orientation, basically what I could do is a series of rotations to get things where I want them. Turns out there are many standards about how to do that. One that many of us know in math and computer vision are Euler angles. Euler angles say you rotate about z. If this was z, you'd rotate, let's pretend z is up. Rotate about z, rotate about the new x, and then you rotate about the new, again, z. All right? For those of you who fly airplanes, I think it's heading, pitch, and roll. Maybe it's boats. I don't know. Heading, you orient yourself. So, you know, northwest. You pitch, that's up and down this way. And then you roll, that's rotation about this way. All right? So you're about the world z, the new x, the new y. There's roll, pitch, and yaw. There's azimuth, elevation, and I guess roll, for those of you who are used to launching mortars. Azimuth, anyway. Basically, there are these three basic matrices, rotation about the x, y, and z. The order matters. Okay, we're not going to worry too much, in fact, not at all, about getting that order. But what it is here are the three rotation matrices written as a function of their angles. There's the rotation about x, rotation about z, rotation about y. I put them in that order. Why? I have no idea. They used to be a different order, but it doesn't matter. The idea is that you can rotate about each of these different axes. Now, whether you pre-multiply or post-multiply, that's an issue. So do we do it the x1, then the y1, then the z1, or the z1, the y1, and the x1? And that depends upon whether you're rotating in the new frame or the old frame. Then is theta positive or negative? So you have to worry about these things really well when you do this, and this is why we build spacecraft in simulation before we build them for real, because when it doesn't work in simulation, the engineer says, I don't know, try negative 20, because knowing which way your angles go is a very difficult thing. How about just an easier way? Once again, to the rescue is going to come homogeneous coordinates. And we're just going to assume that we have a rotation matrix, okay? So here, I took that top equation that PB is the rotated version of PA. And now, instead of the identity matrix in the top left and the offset in the right, we have the rotation matrix here, and that's a 3 by 3. So this 0 vector is a 3 by 1 of zeros. So transpose, it's just 0, 0, 0. This is 0, 0, 0 this way. Okay? And that makes rotation a matrix multiplication. And again, we're using homogeneous coordinates. And to remind you, unlike translation, rotation is not commutative. So now we can do the total rigid transformation. So a total rigid transformation, if I have some point in the A system, I first have to rotate to get aligned in the B system, and then I have to offset it by whatever the offset of the A system in the B system is. That's what this equation says. Using homogeneous transformation, or homogeneous coordinates, we can do this all in one step. So here we have a rigid transformation, and it's really nice, right? We have our point here, we've rotated it, and then we've translated it. And what that says is we have this single matrix, right? This part here is a 3 by 3, this is a 3 by 1, this is a 1 by 3 of zeros, this is just a 1. So our total transformation matrix is a 4 by 4, and it does both the rotation and transfer and translation. Cool, right? It gets better. Thank God. So here I've written what we had before. We have P in the A frame expressed in homogeneous coordinates. Here's our 4 by 4 transformation matrix. Here is B expressed in the B frame. And I'm just going to write this as transformation from A to B. But suppose I wanted to go from B to A. Well, that would be written as transformation from B to A, and I'd have the point P in the A frame. But the way to get that transformation is to just invert the A to B to get me the B to A. And then this transformation takes the value from the B frame back to the A frame. And the idea is that our transformation matrices, our homogeneous transformation 4 by 4s, are typically invertible. And so once we have one that goes from, say, a camera to world frame, we can go from a world to camera frame or the other way around. And this invertibility of homogeneous transformations is very powerful and used all the time. So to review, translation and rotation. From frame A to B, to express this in the non-homogeneous or regular coordinates, we take the location of some point P in the A frame, we rotate it, and then we translate it. In homogeneous coordinates, we write it as this single matrix, where the matrix has the rotation matrix in it in the top left, and the translation vector located here in the right-hand column. And the key is that homogeneous coordinates allow us to write these coordinate transforms as a single matrix. But I've said that 4 times already, so you're saying, like, get on with it already. So now finally we can talk about going from world to camera frame. Here's our equation using sort of non-homogeneous regular coordinates, where the idea is if we have some point P in the world, so that's a point location in the world frame, we have to rotate it oriented to know which way it would be oriented in the camera frame. And then we have the translation from the world to camera frame. Okay? So we have this sort of ugly equation that would get us from a point in the world to a point in the camera. So that P in the C frame, that's now the point in the camera frame. In homogeneous coordinates, it's just expressed like this. The top left 3 by 3 is the coordinate. The right-hand column is the translation. And that whole 4 by 4 is referred to as the extrinsic parameter matrix. Okay? This is the thing that transforms a point in the world to a point in the camera frame. By the way, that bottom row is not so important unless we're doing inverses. That bottom row is what makes this equation invertible. So when sometimes we're doing projection, we're going to use the 3 by 4 instead of the 4 by 4, but don't worry about that till the next lecture. That brings us to an interesting quiz. How many degrees of freedom are there in the 3 by 4 extrinsic parameter matrix? So 12, there are 12 numbers, B, 6, C, 9, or D, 3? All right, well, what's the answer? Well, the answer is still 6. Remember there was 6 degrees of freedom? There are only 3 angles, heading, pitch, and roll, Euler, omega phi kappa, whatever. There are 3 angles that define that rotation matrix. So that it's not 9 independent numbers, right? There's only 3 angles, and then there are 3 translational values. And that's why there are still 6 extrinsic parameters, even though we can use a 3 by 4 or sometimes even a 4 by 4. So we've just basically taken a way of turning those 6 numbers into a matrix form that allows us to apply it to the location of the points in one frame to get the location of the points in another frame. So that ends the lesson on extrinsics or extrinsic, not really calibration, because we're going to do the calibration part. So I should change the title of it. That was about extrinsic geometry. Later we're going to do extrinsic calibration, where we figure out how a camera is oriented in the world. We're going to have to revisit this whole thing when we talk about mapping from world points to a location on an image plane. All right. But before we can do that, we're going to have to talk about, once I have the location of a point in a camera frame, where does that point end up in the image? And that's the intrinsics, and we're going to do that at the next lesson. Welcome back, Introduction to Computer Vision. Today we're going to be talking about intrinsic camera calibration. Last time we said that we're going to do geometric calibration in general, and that there were 2 parts to calibration. The first transformation is from some arbitrary world coordinate system to the camera system, or the camera pose. And this was the extrinsic parameters. And it mapped from world coordinates to camera coordinates, or camera coordinates to world, depending upon how you think about it. When we write it as T, W to C, it takes you from the world to the camera. We expressed it in terms of homogeneous coordinates, where we had a world coordinate P here expressed in that world coordinate frame, and it was homogeneous, so there's a 1 down there, and we pump it through both the rotation component and the translation component to get the 3-dimensional point in camera coordinates. And that world to camera matrix encodes what we refer to as the extrinsic parameters, or the extrinsic parameter matrix. We also said that that encodes 6 degrees of freedom, 3 translation, 3 rotation. Today, we're going to talk about the second transformation, which goes from the 3D camera coordinates to the 2D image coordinates, or the 2D image plane. And these are referred to as the intrinsic parameters. And we'll again come up with an intrinsic parameter matrix. So you might say, whoa, didn't we already do this? We did the ideal perspective projection, where we said that some value u was just going to be the focal length times x divided by z, and v was y divided by z multiplied by f as well. So you might ask, aren't we done? Well, no, because that would be in some idealized world. The first problem, going back to here, is f might be in millimeters. So we might have a 10 millimeter lens or a 50 millimeter lens. But the pixels, the screen pixels, they're in some arbitrary coordinate, right? That depends upon exactly how many pixels we get per millimeter in the sensor. So the first thing that happens is that we introduce an alpha that's just going to scale that value, because we don't really know what f is. Now, sometimes people will give you an f, a focal length, in pixels, which is kind of a weird thing, but what they're actually doing is they're giving you this combined value that is sort of the conversion from millimeters to pixels times millimeters, just giving it to you in pixels. But basically, because they may be in some arbitrary units, we have a scale factor alpha. So that's 1 degree of freedom. But who said the pixels are square? Megan, did you say pixels are square? No. Now, it turns out pixels are more square now than they used to be. They used to be cool, and now they're... No, never mind. Anyway, pixels are more square now than they used to be. It used to be back in television, more of television days, pixels had the same aspect ratio as actually a television. So a pixel was wider than it was tall, and some other things, they were tall and they were wide. They weren't necessarily fixed. In fact, even some CCD arrays that I calibrated once, it turned out that, well, it was almost square. It was like 95% of the height was equal to the width. Right? So because they're not exactly square, you might have a separate scaling factor between the u direction and the v direction. And so now we've introduced beta, so now we have 2 degrees of freedom. But we're not done. Next. Well, you remember we put the center of projection, when we were doing the ideal projection, we put the center of projection right at the camera coordinate system, as if the image was taken so that 0, 0 was right in the middle. But of course, we don't have any guarantee of this, right? The image may have been cropped out of a section of the window, or the location of the image actual sensor might not be lined up with the optical axis of the camera. So we have 2 offsets, a u and a v offset, u0, v0. So now we're up to 1, 2, 3, 4 degrees of freedom. 2 scale factors and 2 offsets. Are we done yet? But wait, there's more. Here comes the really ugly one. We're assuming that the u direction and the v direction are actually perpendicular. What if there's actually a little bit of a skew? So u and v went out drinking one night, and they came back just off a little bit. All right? So that's what's shown in this figure here. The idea is that the ideal u and v are this way. Okay? But maybe the sensor is actually sampled that way and that way. That is, that the actual sampling of UV is are not perpendicular, and they're off by some angle theta. So that's what these equations are showing you here. They're showing you the relationship between the v prime, which is measured, and the actual v, the u prime, and the actual u. And so when you substitute those into those equations we just had, you get this sort of ugliness, okay? So this is the really ugly intrinsic parameter representation. And now we have how many? Well, we've got an alpha and a beta, the 2 scale factors, that's 2 degrees of freedom, a u0 and v0 for the 2 offsets, plus theta, which is the skew. This is pretty ugly, and we'd like to make it nicer, and we're going to do that through 2 ways. First, so here we have those ugly equations, and the first thing you'll notice is, kind of like before, we're dividing the x's and the y's by z, all right? And so that should tell you that, see, I wrote up here intrinsic parameters in non-homogeneous coordinates. Well, guess what? We're going to move to homogeneous coordinates by putting this whole thing in a matrix formulation. So now we can express the whole thing in homogeneous coordinates. Notice that here we have z times u, z times v, z. So later when we convert back from homogeneous to non-homogeneous, we divide by z and we get what we want. We have the x, y, z1 over here, and we have this matrix in the middle. So we can rewrite this as sort of as a very simple equation where we have a three-dimensional point in the camera frame. So remember, we've gone from some arbitrary world frame to the three-dimensional frame of the camera, and we go from that to the homogeneous pixel representation, like that, in the image, and the matrix that takes them from the camera to the image, that's the intrinsic matrix. Okay, so that matrix represents the intrinsic parameters. All right? Now, fortunately, we can make it look even nicer than this. The first thing to notice is that the last column of K, when I write K as a 3 by 4, the last column of K is zeros, and that doesn't really do very much, so we can get rid of it. And then we can do even more. Here we have our kinder, gentler intrinsics. We can use a simpler notation. Like I said, we're going to remove that last column, and we've gotten rid of the explicit thetas and things, and you'll notice that we have the 5 degrees of freedom. We have F, which is focal length, A, which is aspect ratio, S, which is for skew, and CX and CY, those are the offsets. By the way, remember I said that we could have two different scales, right? A scale for one and for U and a scale for V? Or what we can have is a focal length and a relative scale between the two. Normally, we tend to think of it that way, as a focal length, that's the overall focal length of the image, and then if there is a non-uniform relationship between the width and the height, we include that as an aspect ratio. And that's why there are 5 degrees of freedom. Okay? Now, it turns out this can get even easier. All right? And the way it gets really easy is we assume a certain niceness of the universe. Okay? The niceness of the universe that we might assume is if we have square pixels, if there's no skew, and if the optical center is actually in the middle, okay, then we have no A, we have no S, we have no CX, we have no CY. All we have left is F. F is the only degree of freedom left. So when you're doing a calibration, sort of a lightweight calibration, what you'll do is you'll just search for F, assuming that your optic axis is in the middle, assuming there's no skew, and assuming that your pixels are square. Quiz. The intrinsics have the following: a focal length, a pixel X size, a pixel Y size, 2 degree offsets, and a skew. That's 6. But we've said there are only 5 degrees of freedom. What happened? A, because F always multiplies the pixel sizes, those 3 numbers are really only 2 degrees of freedom. B, in modern cameras, the skew is always 0, so we don't worry about it anymore. C, in CCDs or CMOS cameras, the aspect ratio is carefully controlled to be exactly 1.0, so we don't model that anymore either. Well, the answer, as I said, is A, right? We have the F can be multiplied by A for the 2 different scales, or we can have the 2 different scales, but there aren't 3 numbers there, there's actually only 2, and so the answer is A. So now we found the intrinsic matrix, and last time we found the extrinsic matrix. So now we can combine them to get the total camera calibration that goes from a world point all the way through the camera coordinate to the image. So we write down our 2 equations here. We have our intrinsic P prime is equal to K times the point in the camera frame, and our extrinsic, which relates the world point to the camera point. P in W is the world 3-dimensional coordinates. Transformed by the extrinsic matrix becomes the camera 3-dimensional coordinates, which is used also in the intrinsic equation, and then that's converted to pixels directly. One thing to note here is that our world coordinate system is a 4-vector, it's a homogeneous, and we get out a 4-vector, but as we said before, for our K, instead of using the 3 by 4, we can use the 3 by 3, in which case we just use the XYZ of the point in the 3D camera space. We don't have to use the whole XYZ1. That's basically saying that this K can be thought of as a 3 by 4 or a 3 by 3, and when it's a 3 by 3, we don't have to have that 1 on the bottom there. So, putting these 2 equations together, what we have is we take a world point here, we pump it through our extrinsics, so this is a 3 by 4 matrix, okay, which gets us out a 3-dimensional vector, and then we pump that through our intrinsics matrix, and that gets us our homogeneous image coordinates. So this is a 3-vector, remember we said it was Z times U, Z times V, look at that, my U's and V's look the same, divided, and Z, and then we convert it back. And so this whole thing can be written as a single matrix M. M for calibration in some language. I have no idea why it's called M, but we call it M. Just want to write that M in a slightly different way because it's the way that we're actually going to make use of when we solve for this thing. So here we have the same equation written out. You see we have the world coordinates mapped through M gives us the homogeneous pixel coordinates. And what I've written here is I've taken this M matrix, which remember is a 3 by 4, and I said that you can think of it as 3 vectors, each of length 4, transposed as the rows. So each of these rows is a vector. I've also introduced something new here. I don't think I showed it on the slide before. Remember, this is what we said before. Okay, I'm using S as a scale instead of Z, right? And so we have S times U, S times V, and S. And later, to get out U and V, we just divide by S. And I've put this little operator here, but it's just a squiggle with a straight line underneath, sometimes 2 straight lines underneath. And it's what's known as projectively similar. So you'll notice that this vector and this vector are exactly the same except for a scale factor. Right? The vector on the left has been multiplied by S gives you the vector on the right. And remember, in homogeneous coordinates, or using the projective, those 2 vectors are essentially the same because when I use their values, I divide out by the last component. So that's what's referred to as projectively similar. So that's also introduced here. So just finishing, the way I recover U and V is I divide the dot product, the dot of the vector of the point P in the world with the first row divided by that dot product with the third row. That's what's right here. And then to get the V value, I do the same thing, but now with the second row. All right? So basically what we have to find when we're going to do camera calibration is we have to find those M elements. So finally, we can talk about full camera parameters or camera calibration matrix. The camera in its matrix, M, and sometimes it's called pi, and that's what I've written here, as we know, is described by several parameters. It's got a translation, T, of the optical center from the origin of the world. We've got a rotation, R, of the coordinate system. We've got a focal length and aspect, F and A, pixels or pixel size, SX, SY, a principal point, that's the offset, XC, YC, or CXCY, and skew. And in this slide, the blue parameters are called the extrinsics and the red are the intrinsics. And we can put the whole thing together. We want to find this as a sort of a single matrix. M is going to be built up of all of the effects of our parameters. And so that looks like this. Okay? What it says is that M is a combination of translate, this is extrinsic, and rotate. So now we have the point in the 3D camera coordinate system. Project, this is just the extraction of the x, y, z, and then you pump that through the intrinsics. And how many degrees of freedom are there here? Well, there are 11. 5 for the intrinsics, 3 for the rotation, 3 for the translation. I'll get rid of all that scribble. That equation there, that M, that is the full camera calibration matrix. All right. That ends this lesson. What we've done so far is we've derived how the extrinsics and the intrinsics are combined to form a single calibration matrix. And this matrix maps from some arbitrary world coordinate all the way down to a pixel value. What, some XYZ in the world, what UV does it end up in the image? All right? So what are we going to do in the next lesson? Well, the obvious thing in the next lesson is how would you go about finding that matrix? All right? And basically, the requirement's going to be, if I gave you the location of some 3D points in space, and I gave you the location of those points in the image, I should be able to recover that camera calibration matrix. And that's what we're going to do next time. And then a couple of times after that, we'll say, well, if we're less interested in going from a world coordinate system to a camera coordinate system, but instead we're interested in going from one camera coordinate system to another, remember that stereo thing? How would we do that calibration? But first, we go from the world to the image. All right, welcome back to Introduction to Computer Vision. Today, finally, we're going to get to talk about calibrating cameras, where we're going to be calibrating with respect to the 3D world. So Finally, we can get to the parameters themselves. If you remember last time, we solved for the full projection equation that was made up of really a composition of the translation, rotation, projection, and intrinsics. For the rest of today, we're not going to worry about the fact that M has this internal structure till maybe the very end. We're going to think of M just this way. That is, M is going to be this matrix that's going to take your world points in homogeneous coordinates and eventually get you out your image points also in homogeneous coordinates. And what we're going to try to do is find that M. Fundamentally, at the heart of calibration is this idea of having some points whose three-dimensional location in the world we know, and that we identify them in an image. That is, we can find the correspondence between this point in the image is that point in the world, and then we have to compute some sort of a mapping from a scene to the image. And one thing you can do is you can actually put an object like this in the scene that has a bunch of points on it, and you've measured or you know something about the shape of that object, and you know where all the points are. Another way of doing it is to make use of, it's sort of the same math, but it's typically referred to as resectioning, which I'm pretty sure is a term that came from photogrammetry, which is a science that predates computer vision by about a century, that talked about going between images and three-dimensional world, typically used for mapping, cartography, and stuff like that. So in resectioning, which is what we're going to do here, the basic idea is we're going to have some known points. So on the right here, we have a picture of one of our labs, and one of the times one of my colleagues was using a theodolite. That's the thing that surveyors use in order to measure things out, for property or houses. And we set up the theodolite in the lab, and we established a world coordinate system, and you notice we put down these markers. These are actually sort of printouts of what surveyor marks look like. And what we did was we measured the three-dimensional location in the world with respect to this coordinate system of those points. All right? So what that does is that's going to give us a set of points, x, y, z. And then, of course, given an image like this one, we can find the location of uv in that image. Notice again that I'm using the homogeneous version of the points. Here I'm calling it W, so this is W, U scaled by W, V scaled by W, and that's W. And this was that original equation. So clearly, given enough points in the world in the image, I should be able to calibrate, recover the calibration matrix, and here's how. All right, so first some notation. As before, we've got our world times our M is our projective equation. And notice we've got two versions here. And again, what we're saying here is that UV1 is projectively similar to WU, WV, and W. And in fact, in order to get back UV1, I could take WU divided by W in order to get that. And that's actually what's written on the bottom. All I've shown is that UI, that's for point I have to take the product, that's the first row, divided by what becomes the third row. Same thing for VI. So the point here is that I get a pair of equations for every point. For every point I here, I have an equation that goes from XYZ to UI and XYZ to VI. So what we're going to do is we're going to have to solve for this M matrix using a whole bunch of points. Just continuing, I just slid those equations up, and now I've just carried through, just expanded it through. And one thing you'll notice is that every term has an M in it. And for those of you who know anything about linear algebra, that should start to worry you just a little bit, because typically when I want to solve a linear set of equations, I hope that there's some term that doesn't have a variable in it. And we'll see that in just a sec. So I have this pair of equations for each point. All right, writing it again like that. So now the question is how best to solve this. All right, I'm going to write this a little bit different way. So here I have all my variables, and here for just one point I have my coefficients. So notice my coefficients involve capital X's and Y's and Z's. Those are the values out in the world, along with the V's and the U's, which are the points in the image. Now stretch way back into your memory from linear algebra, and you might remember that usually you were solving equations of AX equals B, and you could have more equations than unknowns, and you'd solve to a least square solution. But there was a particular kind of set of equations where the right-hand side was referred to as a homogeneous set of equations when they were all equal to 0. And that's why this is a homogeneous set of equations, not just homogeneous coordinates. These things are all sort of related, and when you get really, really old, you'll figure figure that out. But for now, you can just remember that these are homogeneous equations. So the question is, how do we solve that? Because obviously there's a trivial solution. What's the trivial solution? Well, if a times x equals 0, and I'm looking for an x, well, no matter what a is, x equals 0 would be a solution. So I could just say all the m's are equal to 0. And that would not be a very satisfying solution. So the question is, what's the best way to solve this? So as I said, this is a homogeneous set of equations. Now, when you have a homogeneous set, like am equals 0, and let's suppose you have a lot of equations, well, clearly, what you'd like to do is you want to place some constraint on m, because I don't want to let it be 0. But then, given that constraint, I want to find something that sort of computes the smallest square value of a times m. And that's what's written here. So I'm going to try to minimize the magnitude of am. Now, m is only valid up to a scale. And we know that for a couple of reasons, right? One is you can just take a look at these equations here, right? Since everything's equal to 0, I could just scale m. Or I can go all the way back to my perspective equations, because clearly if I scale all those m's by a value, when I go from the homogeneous to the non-homogeneous, when I divide uw by w, that scale factor will go away. So m is only defined up to a scale, that matrix m, all the little m's. So since it's defined only up to a scale, let's just assume it's going to be a unit vector. Okay, so its magnitude is going to be length 1. And the question is, what's the best unit vector m to minimize the magnitude of am? I'm going to tell you the solution here, and then I'm going to show you that it's the solution. And some of you will have seen this before, and some of you won't. The solution to minimizing am, the magnitude, when m is a unit vector, is, as you all know, I'm sure, because you studied this all the time, you want to take the eigenvector of A transpose A that has the smallest eigenvalue. Of course, you say, I know that all the time. I'll show it to you in a minute. And by the way, this only works when you have 6 or more points, and that should make sense, right? How many degrees of freedom are there in M? There's 11, because there's 12, but only up to a scale. Well, I get 2 equations per point, so I'm going to need at least 6 points. But of course, this thing works a lot better the more points you have. All right, so let's go through the solution. So here I've written as if I only had 2 points, point 1 and point n, with a whole bunch of points in the middle. Okay, so I've got the matrix A times m equals 0. How big is the matrix A? Well, it's 12 across, right, because there are 12 m's. And how many rows does it have? Well, it has 2 times n, where n is the number of points. So it's a 2n by 12 matrix. M is just an m by 1 vector, and here's the 0 vector of length 2n. Okay? So now let's talk about solving that. One step at a time here. All right, so here's our goal, right? We said we want a unit vector that minimizes am, a unit vector for m that minimizes am. So let's do what's called a singular value decomposition, and I'm going to assume that you've seen that before, at least someplace, but the idea is that any matrix can be decomposed into this UD V transpose format where V is a real orthogonal matrix. So in our case, it would probably be a 12 by 12. U is going to be a much bigger matrix. It says orthogonal, but I should be more precise. Each column is orthogonal to each other, so that would be, in this case, a 2n by 12. And most importantly, D is a diagonal matrix, so it only has values in the diagonal, and it is customary to write it as in decreasing order of absolute value, so from the biggest D to the smallest, all right? So we're going to write A is equal to U dV transpose. So minimizing AM is the same thing as minimizing U dV transpose M. Got it? So far, nothing significant other than you have to use your singular value decomposition code from MATLAB. Here comes the first little bit tricky part. That is that the magnitude of U dV transpose M is equal to the magnitude of just dV transpose M. Why? Well, these are just unit vectors, right? The U's and V also, for that matter, are made up of orthogonal unit vectors. So multiplying them doesn't change the magnitude of the matrix. And that's why these magnitudes are the same. And it's also why the magnitude of M is equal to the magnitude of V transpose M. For those of you who think about such things, V in this particular case is a orthogonal, in this case 12 by 12 matrix. You can think of it as like a rotation matrix. So when you rotate a vector, you don't change its magnitude. So the magnitude of M is the same as the magnitude of V transpose M. So that means instead of minimizing U d V transpose M, we can just minimize dV transpose M, subject to, instead of being subject to M equals 1, subject to V transpose M equals 1. Got it? Now you might ask, why are we doing that transformation?
Why are we doing that transformation?
Here's why. It's going to let us do some very cool substitution. So we're minimizing dV transpose M. Let's do a substitution of y equals V transpose M. So now we're minimizing just dy subject to the magnitude of y equals 1, right? Because V transpose M is y, its magnitude has to be 1. Okay, so y is a unit vector. Why? Why not? No, never mind. Because it is, all right? But think about d times y, all right? dy right there. Remember, D is a diagonal matrix whose elements are in decreasing order. So what is the smallest that dy can be? When is it the minimum? Well, it's going to be a minimum when y puts all of its weight, remember y is a unit vector, just in that last element. All right? So the best y for minimizing dy, given that D is a decreasing ordered diagonal matrix, is just 0, 0, 0, 0, 0, 1. Okay, that's the y that minimizes dy. And since we defined y to be V transpose M, then M is equal to Vy. Why? Well, remember I said that V is orthogonal? Right? So when V is orthogonal, its transpose is its inverse. So if y is equal to V transpose M, the inverse of that is just V, so M is equal to Vy. So now we've solved for M in terms of y, but V and y, but remember, y is just 0, 0, 0, 0, all the way 0, 1. So that means that this equation just pulls out the last column in V. All right? Because if I take a matrix, all right, and I multiply it by some vector that's all zeros down to 1, that 1 just multiplies the last column. So I just pull out the last column. So M equals Vy is the last column. And here's something, just because of what we said before, these singular values of A, that's D, well, the singular values of A are the square roots of the eigenvalues of A transpose A, and the columns of V are the eigenvectors of A transpose A. So I could show you this. It's actually pretty, well, I was going to say nah, but you know, if I just write out this, since A is, we know, is written to U d V transpose, okay? A transpose A is just that transpose, so that's V d transpose U transpose. Well, okay, U is an orthogonal vector, so U transpose is also U inverse, so that's an identity. Okay, so that goes away. D transpose D, well, D is a diagonal matrix, so D transpose D is just, I'm just going to call it D squared. It's just the squared values, okay? And V transpose V. So I'm just going to write that A transpose A is equal to V D squared V transpose. And that is the equation of the eigendecomposition where V is the eigenvectors of A transpose A. And by pulling out the very last one, I'm pulling out the eigenvector with the smallest value of A transpose A. Just to recap, given that what we have is AM equals 0 for some long A, what we do is we find the eigenvector of A transpose A with the smallest eigenvalue, and that's our M. That is the set of values that create the calibration matrix for us. Cool. How about another way? Okay. I'm going to show you another approach which in some sense is easier to understand, but it's actually not as good. That's why I showed you the other one first. All right. So here I'm using the same equation again, now using UV1 as being projectively similar to M times XYZ1. But remember, if m can be changed by a scale value without affecting anything, then I could divide all the values by whatever that was on the bottom right-hand corner of m. What I would get out would be a 1 here. So I can just put a 1 in the bottom right-hand corner of that matrix. And the reason I do that is now my equations for ui and vi become this. All right? And what you'll notice is I now have terms when I multiply out, the ones in the denominator multiply ui and vi, which remember, those are knowns because those are the locations of the points in the image. So I now have terms that don't have the variables in them. That's why this is referred to as the inhomogeneous solution. And one of the reasons this is not as good is suppose the original M23 was supposed to be much, much smaller than the other values, that is, close to 0 compared to the others. Well, you've just set a number that was supposed to be really close to 0 to 1. That's dangerous with respect to numerical stability. So in general, and also in terms of overall minimization, doing the singular value decomposition or doing the eigenvector finding on A transpose A is the preferred method. And by the way, it's one line in MATLAB, so you might as well just do it. So what I just told you is referred to as the direct linear calibration or transformation method. It has a couple of advantages. One is it's pretty simple and to formulate and to solve. Like I said, it's literally, you just take your points, you make that A matrix, you then do some SVD, you pull out the column, bang, there's your M. Now these methods are referred to as minimizing an algebraic error, because essentially what we did was we set AM, we fixed M to be a unit vector, and then algebraically found the M that gave us the smallest algebraic magnitude of AM. There are some disadvantages to this method. First is that it doesn't directly tell you about the camera parameters, but we'll fix some of that in just a minute. It's also approximate because that M was based upon a particular matrix based upon pure extrinsic and intrinsic projection. What if we had something like radial distortion that we could actually model, but we couldn't model within our projective transform equation? How would we do that? Suppose I actually knew the focal length, right? I went out and bought a really expensive lens with focal length 3.746586, really precise millimeters. I don't want my M screwing with that. It needs to stay that value. I want to come up with the minimum solution using that precise value. And then finally, another problem, I put down mostly, I think it's just another one of those problems. It's not actually minimizing the thing that I really want minimized. It's minimizing this kind of cute algebraic trick that I had. So what is it that I actually want to minimize? Clearly, the amount of weight I put on every holiday. But besides that, what? Okay, that was not even a funny joke, but it was going too long without any jokes. So what is the right error function? Well, we refer to this error function as the geometric error, and it works as follows. Let's suppose I have some points in the world, capital Xi, and here they are shown in yellow. And furthermore, let's suppose I have an image, and I know where those points are in the image, and those are the red Xi's here, and these are these little red points here. Now, when I specify a camera projection, some sort of an M, right, what I'm saying is I know where those capital Xi's, the real points, are supposed to project to the image plane. And what I want to do is I want to find the M that gives me the smallest distance between the predicted Xi's and the ones that I actually found. And that's what this equation here says. What it says is we have an error function that is a sum of the distances between the observed points, those are the red Xi's, and the predicted image locations, the white Xi's here, of where the particular M predicts that the points in the world would land in the image. And what I want to do is I want to find the M that minimizes that value. And now what's kind of cool is I might have a more complicated mapping from points in the world to my 2D points that include things like modeling radial distortion, but fix for me the focal length. The idea is I'd have some great big nonlinear function that does the full projection. And what I want to do is I want to minimize this error function by manipulating the parameters of that big nonlinear function. And you might do that using your favorite Levenberg-Marquardt or some other way of doing nonlinear minimization. So if you read about this in a book and it says the gold standard, well, the gold standard of this type of work is the book on multi-view geometry by Hartley and Zisserman. What they refer to as the gold standard of calibration is, given some number of points greater than or equal to, but should be greater than 6, where you have 3D to 2D point correspondences, the way to find, they refer to as the maximum likelihood estimate. We could talk about why that's the case later. I'll tell you right now. You're assuming that the place that you located the points in the image was perturbed by a little bit of Gaussian noise, so you maximize the likelihood by making that distance as small as possible, and you want to minimize the square error if it's a Gaussian error. So the way you do that is as follows. You first compute a linear solution. Now, Hartley and Zisserman talk a little bit, and this is for those of you who are going to be more involved in doing some of this. What you might want to do is, if you're measuring your points out here in meters, you might have some big numbers or small numbers depending upon your coordinate system. Your size of your image, you may have different pixel values. They do a normalization so that everything sort of goes between 0 and 1 to try to get numerical stability. So when they do that, they create new external world points and new image points. You can do that or not. Then what you do is you solve the thing I showed you before, the direct linear transformation using typically the eigenvector approach. That gives you a starting point for the M matrix, which gives you a starting point for your nonlinear function. And then what you can do is you can try, using the M, you project the points, and then you can minimize that total distance, that's what's written down below, using, like I said, your favorite nonlinear method. After you've done all that, if you've done the normalization, you have to denormalize or translate back from the normalized methods. So that's how you get out your M. And that's what they refer to as the gold standard algorithm of calibration. We only use bronze, which is why in your problem set, you're going to use just the direct linear method. And you're going to see that even without, I will tell you this, that the first time we did this, we had people do the normalization, and it turns out the normalization buys you some, but not a lot. When we do it this time, you can use the normalization or not. So now we have M. Now we know that M encodes all the parameters, the extrinsic parameters and the intrinsics. So we should be able to find things about the camera from M. For example, the focal length, which would be an intrinsic. Or how about the camera center? In order to be able to do the projection, the camera center, remember the translation vector that translates from the world coordinate to the camera center? That, if we just knew that translational value, that would tell us the location of the camera center in the world coordinate frame. So we should be able to get that directly from the M matrix. So I'm going to tell you about two ways of doing that. Sort of the pure way, which is beautiful, and then the easy way. So we'll start with the pure way. Here's a slight change in notation just to pull out our parts. Okay, so we have our matrix M, and I'm just going to assume that M, which is a 3 by 4, is going to be made up of this 3 by 3, which I'll call Q, and B is just this 3 by 1. It's just a vector. Okay, so we've got Q and B. I'm going to claim that the center, C, which is a point, which I'm going to represent as a vector, is in the null space of the projection matrix. And what that means is that if you multiply M times C, it equals 0. And if you found such a C, that would be the camera center. And you should just trust me. Okay, maybe you don't trust me. Let me show you why that's true. All right? It's really pretty simple, except drawing it is painful. All right? Let's suppose I have some camera center C, and I've got some plane, and I have some point P that's out here. So I have a ray that goes from P to C, and I'm going to have a point X that's somewhere on that ray. Okay, so that's where X is. All right? So that's all that this equation says, that X is equal to something that's a blend between P and C. Right? Lambda times P, 1 minus lambda times C. So given some M, that's the camera, the projection, all right, of X is just Mx, And just by linear algebra, that projection is just lambda mp plus 1 minus lambda mc. Now, for any point P, all the points on that ray have to land at the image of P. So any point P, all the points on this ray have to land at the same point on the image. Okay? So any point x along here will land at that same point, no matter what lambda is. Well, if this equation has to be true no matter what lambda is, and it has to land at mp, because lambda might be 1, that means that this value, mc, has to be equal to 0. So if c is the center, mc equals 0. And that's why I said before that the center C can just be found by finding the null space of the projection matrix M. That wasn't too painful. But suppose you actually wanted to do something useful. What would be the easy way of doing that? Well, the easy way is I just give you the formula. So if M is equal to QB, as I said before, then the center is just found by taking this quantity above that quantity in a vector. So this is remember Q is a 3 by 3, so minus Q inverse is a 3 by 3, B is a 3 by 1, so this is a 3 by 1, and then I add the 1 there. That is the vector that is the camera center in the world coordinate frame. So if I made, the corner of that table that you can't see, there's really a corner over there, if I said that's the origin, all right, and this way is X, and this way is Y, and that way is Z. And then I have a camera here, and I took a look at a bunch of points here, and I gave you the value of those points in this coordinate system. And then I located those points in my image plane. And then I did all that math to compute that M vector, and that M matrix. And then I pulled out the 3 by 3 and called that Q, and 3 by 1 and called that B. And then I took minus Q inverse times B over 1. That vector would be the actual location of this camera in that world coordinate system. Pretty cool. Finally, and this is the half bit that I was telling you about, there's an alternative way of doing calibration, which is pretty cool. And in fact, it's really what everybody is using today, because typically you don't have all these points. And it's a way of getting the intrinsics, and then if you know where you put these checkerboards, it's extrinsics. Basically, what you do is you take a checkerboard and you move it around, and you can end up calibrating the camera with respect to that checkerboard. The reason everybody uses that these days is that there's, first of all, you can print out a checkerboard, and the checkerboard has to be on a plane. Well, that's easy. You print out a checkerboard. You got to make sure your printer doesn't screw things up. You got to make sure that it actually comes out that squares are squares. You mount it on something that's a nice piece of rigid cardboard or foam core, and you don't have to know the positions and orientations in order to get the intrinsics of the camera, and then later you can get the intrinsics as well. And why does everybody use this? Because the code is easily available online. OpenCV supports this directly. We list here a MATLAB version of it. If you go to Zhengyu Zhang's website, he's like Dr. Calibration. He did spectacular work for us, these etc. in calibration. I'll also tell you that there's something cool you can do, and in fact, a student of mine, Kelsey Hawkins, did this, and I think the code is made publicly available. If you take a checkerboard and you mount it on the end of a robot arm, and remember, a robot knows where its arm is in terms of its coordinate system. If you also know, let's say, the offset of that checkerboard from the end effector, the hand, then what you can do is with a camera, you can just move that checkerboard around using the robot. And of course, we know the 3D location of the checkerboard at every point in time that we take an image. And so by taking those images of the checkerboard, you end up calibrating the camera to the robot's coordinate system. So it's a cool use of doing this directly within robotics. So this concludes the lesson on calibration. In the homework, you're going to use the theory we developed for the direct linear calibration, and we'll give you those images that have the three-dimensional locations of the points, and you get the images, and you have to solve for the calibration. And it's interesting that you can actually recover that relatively precisely. In the next lessons, what we're going to do is we're going to move away from the notion of rigidly calibrating the camera to the world, and instead we're going to talk about the relationship between multiple cameras. specifically starting with 2 cameras. And that's going to eventually get to the point where we were talking about in stereo, that if you know the relationship between cameras, that you can know where the epipolar lines are. So basically, if I gave you some corresponding points, you should be able to solve for the relationship between the cameras that will allow you to find those epipolar lines. And that's what we'll be doing over the next 3 or 4 lessons.